Okay, hello everyone. My name is Piotr Tompalski. I'm the person on the left, the handsome guy on the left. But this work I'm presenting today is not only my work, it's the work of an entire team of people who I work with, specifically John White, Mike Wolder, Sean Hermosia, Werner Kurtz, and Niklas Kups. And I will be talking about how we use remote sensing in forest management and monitoring in Canada specifically. So the context is forests and all these other buzzwords, but also Canada. This is sort of about me slide, because I know that not all of you read all of my papers, so I compress them in this word cloud so that you know what I work on, what are my research interests. I did my PhD in Krakow, and then I left Poland to do a one-year postdoc in Canada that turned into a 10-year stay in Canada. And now I'm actually working in Canada, having Canadian kids, and still debating, should I come back or should I stay? We'll see. Okay, so shortly, the outline of this presentation. I'll be briefly talking about forestry in Canada, what it is and why it may be different, or what are the similarities between forestry in Poland or forestry in Europe and Canada. One word about Canadian Forest Service, where I work, and then mostly about remote sensing and forestries, focusing on large area monitoring, and then talking a bit about enhanced forest inventory. If you are completely bored now, I want you to remember just one sentence from this presentation. Canada is big and has lots of forests. When I came to Canada, having Polish experience, Polish knowledge about forests in Poland, I didn't realize how important this is. Canada is big and has lots of forests. How big is Canada? You can see the overlaid two maps of Canada, overlaid map of Canada over Europe, and then different European countries fit into Canada. This really is important to remember. Many of the decisions that Canadian foresters make come out from this statement that Canada is big and has lots of forests. How big is Canada and how much forest there are? Well, I can tell you all these numbers. You can read the numbers. That is almost 1 million hectares. But I also converted into units of Poland, right? Maybe it's easier for you to understand, right? So 31 times Poland, that's the size of Canada. And if you think about the forests only, then 12 times the area of Poland is how much forests we have in Canada. It's 10% of global forest, 30% of global boreal forest. Important to remember is that almost 90% of Canada forests are publicly owned. Another thing worth mentioning is that not all forests in Canada are managed. We have this distinction between forests that are managed and forests that are unmanaged. The unmanaged forests are forests where, there's no management, right? There's no forest activities performed. Those are usually forests located more to the north, low productivity forest stands. Differences between Europe and Canada. Ownership, I know this is different. I say on the slide that ownership mostly private in Europe. I know this is not true for Poland, but overall for Europe. In Canada, as I said, 89% of forests are public. Management, very intensive in Europe with small forest management units, extensive in Canada with very large forest management units. That was one of the shocks that I experienced myself when I came there, seeing cut blocks that are over 200 hectares in size. That's something you won't see in Europe. Canadian Forest Service, that's where I work. It is, well, everything that Krzysztof said about forest, how do you translate? Forest Research Institute, this is the Blanche in Poland, more or less the same. It's the same concept, right? A science-based policy organization that hires people to advance science, but also implement the science and design tools to help foresters with management and the decision making. What are the information needs for forest monitoring? Government of Canada, and that sort of also relates to Canadian Forest Service and what we do there, has international reporting commitments. Every year we need to prepare and submit a report summarizing the national forest inventory, for example, in carbon accounting data. These information need to be consistent, need to be spatially explicit, it need to be detailed, and mostly need to be national in scope. And as I said before, Canada is big and has lots of work. We also are interested in the trends. How are the forests changing over time? So when you think about all of these highlighted words, you can start seeing what kind of remote sensing or spatial data we need to achieve this goal. When I was preparing this presentation, I also wanted to include this slide. What are the challenges? What are the issues in Canadian forestry? But I am a very lazy person, so I just asked ChatGPT, and this is the output. Surprisingly, it is actually very accurate. These are the challenges that Canadian forestry, and I'm sure not only Canadian forestry, is facing currently. Climate change, very important. What do we do with our forestry? How do we prepare for the changes in the climate, right? Forest fires, I'm sure you watch the news and you see what happened in Canada last year. That was the worst. Also pest infestations, biodiversity loss, sustainable management. How do we balance logging with conservation, and many other issues. I want to highlight one, the one from last year. So something that maybe some of you saw on the news. 2023 was the worst fire year in Canada, I think, ever. And I tried to look up the actual data. What was the actual area burned in Canada last year? And I couldn't find any official number because the official numbers end at 2022. And then I found from, well, different sources and wanted to add that bar to this graph to show 2023. But I couldn't. It was too large. So I needed to shrink this graph a little bit and then added that bar, right? So last year, you can see how many fires there were in terms of area of Poland. Over half of Poland burned last year in Canada. And this is not only some number or some area, or some forests are burning somewhere in Canada. This is affecting everyone. It was affecting me as well. I suffer from asthma. It was horrible because every day I walk out of my apartment and where's the pointer? And everything looks like this. And we have this beautiful sunsets in the middle of the day. Okay, let's go back to remote sensing and the interesting stuff. So how can remote sensing help? Some examples. Of course, this is not everything we can do with remote sensing, just some examples of the work that we do at CFS. We start with the needs. We ask the questions, what are the attributes, for instance, attributes that Canada's National Forest Inventory or carbon accounting or other program need? And some of the basic attributes, land cover, crown closure, age, species height, volume, biomass, we can think, how can we get those from remote sensing? Well, we can also specify a bit more detailed. What are the disturbance-related attributes that we can extract from remote sensing? Information about disturbance year, disturbance type, what is the land cover before the disturbance, what is it after the disturbance? How is the recovery, forest recovery after the disturbance? So you can start thinking what kind of data we could use to extract this kind of data, this kind of information. The data that would be national, that would give us national coverage, that would be a time series to allow the monitoring, and then would also allow us to get the substance level of detail, and also would be free, of course, Landsat, right? The Landsat time series is one of the most important data that we can use for monitoring forests in Canada. Landsat time series, just brief information how we work with this type of data. we stack all of the images, stack all of the pixels, and analyze every pixel one by one, and see how this pixel, how the reflectance changes over time. And many of the pixels, we can see that the reflectance stays more or less the same over time. So we know these forests didn't change, didn't experience any disturbance, or more or less nothing happened, happily growing. But then there are also pixels that will show us some changes, some sudden drop in spectral index or reflectance. And then we can see, okay, this is probably a disturbance. Something happened in that location, probably a disturbance. And when we analyze these trajectories and compare them and classify them, then we can create maps showing us the year of the disturbance, so the graph in the middle, and what was also the maps showing us the type of the disturbance. Was the disturbance fire? Was it a harvest? Was it a so-called non-standard placing disturbance? And this is very important, a very, very important product for Canada. You can see this on a sort of smaller scale, level of detail. If you look here, top right, you can see harvesting happening. If you look at some location here, sorry, the pointer doesn't really, but here, there's a fire that happens 1 year, and you can then see this fire here. And then when you look at the legend, you see that this fire happened 2011. We can have this kind of information for the entire Canada, right? This program that this product is called National Terrestrial Ecosystem Monitoring System, and comprises of many products. So we have land cover information for every year since Landsat time series began, so 1984 up to now. We can have information about disturbance year, disturbance type, post-disturbance recovery, pre-disturbance condition. A lot of attributes that are very, very relevant for forest monitoring in Canada. Of course, these maps that I show, this is a huge area, but remember that the level of detail here is 30 meters. We have this information for every 30 by 30 meter pixel everywhere in Canada. Something also very important, very interesting, recent developments, species. I wouldn't say we because I wasn't involved in this, but Canadian Forest Service, my friends developed this map, this product, species classification. For every 30 by 30 meter pixel, they classify the dominant species. What is really important is that this is not a binary classification, but we have information about class membership probability. So you can have single species maps like this showing you how probable it is that, for example, black spruce will grow in that given location, right? Or trembling aspen. For me, this is very, very cool and very important. Going forward, stand attributes for every pixel. We know we have disturbance, we have land cover change, we have species. We also have stand attributes like above ground biomass, volume, height, canopy cover. Those were products of models that linked plot information with LiDAR and then were extrapolated using Landsat data to entire Canada, right? So for every year since 1984 up to now, we have information about the biomass of every pixel. This is huge. We can have a time series of biomass for every pixel. Very, very important. And then most recently, forest age, also at pixel level. 30 by 30 meter, every pixel, we have an estimate of age, developed from Landsat time series. So now question for you, how accurate this age is? What do you think? Is it plus minus 1 year, plus minus 10 years, plus minus 50 years? Of course, the answer is that it depends. You know that we know that Landsat time series started in the data we work in 1984. So if the disturbance happened during that time, we know that the new stand the age starts, let's assume, a year after the disturbance. So the accuracy in that period is very high, let's say plus minus 1 year. But for the older stands that weren't disturbed in the so-called Landsat era, then we need to do some modeling, and then the accuracy drops to more or less plus minus 30 years. Application of all of this, when we combine it, we can do some segmentation and assign all these attributes to a table. Foresters, they prefer polygons. Very often they don't like rasters. They like to have polygons they can click on and look at the table and see summaries of all the attributes that we deliver them in the raster format. So if that's preferred, sure, no problem at all. You have your polygons and you have 500 attributes that you can pick and work with. So to summarize this program, this NTENS program, this is my personal score I gave how good these attributes are when extracted from Landsat time series. Land cover, very good. But all the other attributes like trunk closure, age, species, height, volume, biomass, there are other tools that can give us better accuracy. We can have them at the national level, but very often that accuracy could be better if other tools were used. All the information related to disturbance, very, very good. So what is this other tool that can give us better accuracy of those attributes that I highlighted in orange? Well, of course, everybody's favorite, airborne laser scanning. Airborne laser scanning, the accuracy of the model attribute is much higher. I know that it is extensively used in Poland, so I don't have any, introductions of what it is. It is a bit more challenging to get to a national coverage in Canada, airborne laser scanning, and that I don't think anybody is planning that. But there's a lot of data already acquired, and this map shows you the ALS coverage, and also when the data was acquired, which provinces acquired how much, and so on. This is, of course, several times more than the area of Poland. And how it is used, it is mostly used to develop so-called enhanced forest inventory. So forest inventory at pixel level that gives us raster maps showing attributes like height, basal area, biomass, volume, canopy cover, anything you want at the pixel level. It is accurate, it is detailed, and can cover large areas. The concept of EFI is to link plot attributes that we measure in the field with attributes of point cloud, so-called point cloud metrics, that we use to develop models. So we link those point cloud metrics with the attributes we measure on a plot. And then once we have those models, we can apply those models for the entire area where the ALS data was acquired. And if we talk about the status of enhanced forest inventory, it depends on the jurisdiction. Every jurisdiction in Canada is very independent, and it is up to the jurisdiction to decide how they use LiDAR data, how they use EFI, how they develop EFI, what methods they use. So it's very unfortunate. There's no Canada-wide standard on how LiDAR should be used in forestry. Every province does it sort of independently. In some jurisdictions like New Brunswick or Quebec, they already have complete coverage of their provinces, and they use it operationally. It's amazing. They just switched, and they like it. They want more. They see it as the current standard. Other provinces, they are sort of on a path to the operational. But some provinces like Newfoundland, they are still in the research stage. And as I said, they use different standards, different modeling approaches. They derive different attributes in different formats. Some use it in-house, meaning by their own. Some provinces hire companies to do the EFI for them. So the next stage, if we think about LiDAR and we think about provinces being happy with the LiDAR and wanting more of it, is to look at the change in forest attributes, using multiple LiDAR acquisitions and then looking at the change in those attributes. Here is this image shows you 2 point clouds acquired over the same area 4 years apart. You can think which one was first and what happened. Of course, the orange was first, and then the trees were cut down. Something important we found that when working with multiple multi-temporal airborne LiDAR data, it is very important to first check, are the data we call it harmonized, meaning do they match? Very often the vendor who delivers the data delivers it in the different coordinate system. Maybe there's some poor quality assessment done. And we found that very often over the same area, the differences of this the coordinate was over 1.5 meters. It doesn't happen all the time, it happens sometime. But when we think about using these data to study changes, especially in height, this is crucial. How can we use this multi-temporal LiDAR data? Where one thing is to, I call it retrospectively estimate growth. So we have these two acquisitions or more, time one and time two, and we can look in the past. We can subtract one point cloud from another, say, and look what changed and how much. Another way of using this data is to try to link those changes with growth models, for example, and try to forecast the changes into the future. So the easiest example, we have two canopy height models derived from two different data sets over the same area. We can see what changed and how much. We can subtract the two canopy height models and see, oh, this pixel grew by 1 meter, this pixel grew by 1.2 meter, this pixel shrunk by 20 meters, probably a clear cut. Very easy analysis and very informative. If you want to go forward, then we can look at, for example, changes in the attributes that I told you about. At every pixel, right, we have estimates of attributes. We can have those estimates at time one and time two. We can subtract them and see what is the change in volume, what is the change in basal area, and so on. If we detect the trees in the first stage and the second, we can also do this kind of analysis at the tree level. It is much more challenging, but possible. So then we can also try to link those multi-temporal data sets and information extracted from those multi-temporal data sets with growth models. And there are many different ways of doing that. I won't bore you, but I thought this graph was cool, so I still wanted to include it on the slide. By doing that, the most important thing on the slide is that by doing that, we can forecast the changes into the future. If at time one, pixel was 20 meters tall, and at time two was 21 meters tall, we can fit a model that goes through those 2 points and forecast the height of the stand at a given age. And we can do that with every other attribute as well. And when we do that, for every pixel, we can have this, we can forecast this information for every year and create animations that visualize this process. You can see these are 4 different attributes: height, basal area, volume, and number of trees. The colors are changing, but sometimes very slowly. But there's also this little graph that shows you the change over time for a pixel in the center of this figure. I find it very cool. I've included this slide on every of my presentation, and I will play it 3 more times so that you enjoy it with me. It was a lot of work. So this is yield curves linked to every pixel, but the yield curves were already existing. The growth and yield model is a growth and yield model that already existed. We just supplied it with information that came from LiDAR data. But what if we go a step further? What if we develop a yield curve using a remote sensing data? What if we don't rely on an existing model, but build our own? Maybe you remember from the beginning of the presentation where I was talking about the Anthems program, the Landsat-based pixel level estimates. that we now have species, we have time series of above ground biomass, and we also have age that sometimes is plus minus 1 year, sometimes plus minus 30, but still we have it. We can combine these three products together and develop yield curves for every species in Canada. That's something I managed to do recently. I'm very proud of. Another animation came out of it. Most importantly, that was a joke. The animation is not only the product that's a result of the research, but most importantly, we now have yield curves developed entirely from remote sensing data. For every area, this study area was only in Alberta, but you see it divided, this area is divided into this 150 by 150 kilometer tiles. And you see they are arranged in this shape, right? And the same shape is this here, this big graph on the right. For every species in every tile, we have an independent growth and yield model developed. How all of this, my last slide, links together and why we even do this. Well, one of the programs that Canadian Forest Service is involved in is the National Forest Carbon Monitoring, Accounting and Reporting System, so monitoring carbon in Canada. You see this carbon monitoring program, it requires a lot of different inputs. It requires disturbance, information about disturbance events. It requires land use changes. It requires growth and yield curves. It requires detailed forest inventory. And I think I talked about all of these inputs being possible to derive from remote sensing data. And that's the big change that is happening currently in our carbon monitoring program, that more and more of the inputs to that CBN CFS3 model will come from a remote sensing data. It won't be a polygon level analysis, it will be a pixel level analysis for the entire country. Much more accurate and much more detailed. I think that's it. Thank you.
Thank you for the invitation. I am Saverio Francini, and I'm an assistant professor working at the University of Florence. I'm very sorry to not being with you. It would be very nice because I see several friends in this conference, and it's sad that I cannot meet you again, but I hope there will be other opportunities in the future. Anyway, in this presentation, I'll talk you about remote sensing and ground data integration for forest disturbance and attributes mapping. As you know, the main source of information about forests are national forest inventories. So they are the main source of forest information and also the official source of forest information. While national forest inventories are, of course, key and crucial for forest monitoring, they also face some limitations. So we have different methodologies depending on the countries. We have also high data collection costs. And then we have, as many of you know, difficulties to assess the data. And also, yes, and also an important thing is that national forest inventory data is often updated every 3-5 years. Some countries update forest inventories data every year, but not all of them. On the other hand, now and more than ever, there is the availability of remote sensing data. So remote sensing data and also the Copernicus program provide very, very important information and very useful data to monitor European forests. And in this context, with this huge amount of open access data and with the availability of cloud computing platforms to process this data, the integration and of remote sensing data with ground data became more operational. And indeed, complementing national forest inventory data with remote sensing data may allow to increase the frequency with which data is delivered and the spatial resolution with which information can be provided about forests. When you want to monitor forests using remote sensing optical data, the first issue that you have to address is to obtain cloud-free composites over large areas. So when you look at Sentinel, in this case, Sentinel-2 images, as they are acquired, you can see that there are clouds. You can see that different scenes are acquired over different periods, or I mean, over different dates. And when you want to cover the whole of Italy, for example, or also the whole of Europe, you have to obtain consistent data over the whole study area. Sorry. So the first thing that you need to do is to mask out clouds and to obtain these cloud-free composites over the whole study area. There is a method to do that. It is not only, it isn't the only method available, but it is one of the most commonly used methods. It is the best available pixel that was developed by White et al. In 2014. And it is about masking out clouds, and then after having defined a specific time window, selecting among the available pixel informations the best one. The best observation is defined based on several different criteria. For example, the distance to clouds, the opacity of the pixel, the distance in terms of day between the acquisition date of the pixel and the date that we want for our composite. And there are also several articles that try to adjust these parameters or to use different parameters to define which is the best pixel that should be selected. We wanted to use this method across Europe. And to do that, one important thing is to have the capability of processing a large amount of data. In this context, there is the Google Earth Engine cloud computing platform that is a game changer in the remote sensing community. Google Earth Engine was developed in 2015, about 2015. And this article where the Google Earth Engine platform was presented was published in 2017. As you can see, it's crazy to see that there are already about 6,000 citations of this manuscript in Scopus, and that if you look at Google Earth Engine and to find some articles, you can find about 4,000 documents using Google Earth Engine. So Google Earth Engine is a cloud computing platform that allows you to process a huge amount of remote sensing data easily, quickly, and is very useful also to share the outputs with other colleagues. So we used Google Earth Engine to implement the best available pixel composite procedure, and in this way we are able to construct these composites in over large areas. This is, for example, Canada. Indeed, this activity was carried out while I was in Canada in the laboratory of Nicolas Coups, and where I also was able to meet Piotr. So now that the method is available on Google Earth Engine, you can use it everywhere in the world. For example, you can use it to calculate the normalized different vegetation index all the whole of Europe. And but at a certain point, we decided to try to assess more in depth these composites, and we realized that actually there are many available different methods to calculate composites. But what it was actually missing was an exhaustive method to assess the quality of these composites. So we developed this method to assess the quality of composites based on 5 main criteria. And one of the main criteria is what is shown in this slide on the right, and is the acquisition date. So you can see that each pixel is scored based on the date from which the pixel came from. So in this way, we were able to compare, for example, BAP, best available pixel, and medoid composites, and we found strengths and weaknesses in both of them. But anyway, we found that the BAP BAP method was more useful to construct temporally consistent composites. And having temporally consistent composites is a very important thing when you want to monitor forest disturbances. So we using our method, we obtained best available cloud-free composites over the whole of Europe between 1984 and 2023. Okay, when you have a time series of remote sensing data, what you usually want to do first is to predict forest disturbances, forest changes more in general, because you can have negative but also positive changes. And to do that, there are several available methods. These methods aim to detect segments and vertices over a time series of a photosynthetic activity index. We implemented our own method on the Google Earth Engine platform. Again, it is similar somehow to the C2C method that was implemented by Mozilla and colleagues, but it has some main differences especially due to the implementation in Google Earth Engine. So we have to develop different algorithms due to some limitations of the Google Earth Engine platform, and also linked to the fact that we had to use a different programming language. But after several research and effort, we were able to find a very good forest change detection algorithm. Our aim was to do not remove too much noise. So, for example, in Tuscany, we have forest harvesting that are followed by a very rapid spectral activity increase. And in many of the existing forest disturbance algorithms, these kind of changes were removed, were masked out, and were considered as noise because they were somehow similar to the noise that is produced when a pixel is covered by an undetected cloud. So we tried to address this issue. And another thing that we wanted to do is to develop a method that is able to detect also low magnitude changes. For example, so low magnitude and short duration changes. That is the example, for example, of drought. Here we have an example of the output looking at the Via storm, that it was a windstorm that occurred in Italy in 2020. And as you can see, the spectral activity increase occurs over more years because the remaining wood on the ground is removed the years later to try to manage the forest and to address the issues caused by the windstorm. Here we have an example of the forest harvesting I was talking about. So here we are looking at Coppice Forest in Tuscany. Here we have an example of on how they look like, and you can see that they are followed by a very rapid spectral activity increase. So this was actually not very rapid, this example, but sometimes you can see that, or the year later, you have already recovered the 80% of the photosynthetic activity of the forest. So it is somehow very similar to the spectral behavior of noise. That's why we had to adjust a lot the specking algorithm, that is the tool that is used to remove noise from time series. Here we have an example of a huge forest fire that occurred in Sardinia, and you can see that the magnitude, so the normalized burn ratio decrease is very large when you look at forest fires. Here we have an example of the user interface of forest disturbance that we developed, and you can see that here you can see in black forest harvestings, so forest disturbances with large magnitude, and in green forest disturbances, forest changes actually with very low magnitude. So some of them can be disturbances, some of them can be just for photosynthetic activity decrease due to two different seasons. But using the parameters, you can remove low magnitude changes, for example, and you can also try to classify these changes based on different parameters that are available. One important thing that we wanted to do is to exploit Google Earth Engine and to maintain as much as possible information on these forest changes. So we are not just mapping forest changes, but for all of forest change, we are calculating the magnitude, the intensity, the duration, the persistence of the disturbance, but we are also maintaining the Landsat bands of the forest disturbances. So we are trying to maintain the spectral information of these forest disturbances. For example, this picture that you are looking now, this GIF, is showing you the forest disturbances that occurred in the last 40 years in this study area. And you can see that everything seems brown. It is because you are looking in a single image at all forest disturbances that occurred in the last 40 years. And the color is the red, green, and blue composite. So everything is brown because when these forests were harvested, they were brown. So when you have forest disturbance data and information that can be derived from these disturbances, and when you have also Landsat composite for the whole of Europe, you can try to use this information to predict actually LiDAR information, because to obtain information on the three-dimensional structure of forest, LiDAR is much better than optical data. And on the other hand, LiDAR is very useful to construct model with optical data, because you have LiDAR data over larger areas than the national forest inventories, for example, and because you have LiDAR data at a spatial resolution that is more consistent with the spatial resolution of Landsat, for example. And this is what this article suggested. This in particular, this one. So using the data we had, we tried to construct a machine learning approach to predict airborne laser scanner metrics. And this is very useful to obtain maps of canopy metrics. These are some of the metrics that were suggested in a study by Matash et al. We increased the predictors that we wanted to use, and then we used a neural network. The inputs of the neural network are these predictors coming from the composites and then the forest disturbance metrics and changes, and the outputs are in a single model all of the airborne laser scanning percentiles. So it is just one model that tries to predict several response variables. To do that, of course, we divided our data sets of reference data into training, validation, and test. We actually had 5 study areas. This is an activity that was carried out within the EFINET project, also with Chris, which was one of the colleagues in which was involved in this project. And then the method was evaluated on the remaining data. And as you can see, we found let's say, quite good results. So we tried to predict using Landsat data the canopy 8 model percentiles, and you can see that we found quite good outputs over the different study areas. This is, for example, the Bialowieza forest, and this is, for example, the outputs in Netherlands, in Switzerland, and here the outputs in Tuscany. Here we have a quick comparison of these results, and then we also tried to use the airborne laser scanning metrics we predicted to predict again the volume and the basal area. So we have to extrapolate from the volume and the basal area, from the airborne laser scanning metrics, the volume and the basal area. That is what was done in the Matash et al. Paper. And again, we found quite good results. So as I showed this in these slides, but as also many scientific articles show, there are a lot of available methods that can be used to integrate remote sensing, national forest inventory, and also LiDAR data to obtain very useful information on forest at a very detailed spatial resolution and frequency. But there is also the forest species is another important thing that you want to monitor about forest. And in this sense, we try to develop our own method. So we try to fit using Sentinel-2 time series harmonic functions. So this is an example of the NDVI index in red. And as you can see, there is some noise, of course. So we try to fit this function, an harmonic function, And in this way, we try to obtain very consistent predictors over the whole of Netherlands. In this case, the study area was Netherlands. From this function, you can calculate the amplitude, you can calculate the phase, and you calculate also other several important parameters. And the hypothesis is that these predictors are more useful to predict, to study the phenology of the pixel and then to predict for a species. So they are the hypothesis is that these predictors are better with respect to more standard cloud-free composites, such as the best available or the medoid composites. We trained our model. We found actually that as expected, the harmonic predictors allowed to increase the accuracy of about 10% with respect to medoid composites in this case. And then we applied the method over the whole of Netherlands to obtain this 7 species group. Another thing that we wanted to do is to try to exploit as much as possible the national forest inventory data and to take the most from them. So we developed a method to try to compare and to aggregate national forest inventory and remote sensing statistics over these cells, these 10 kilometer cells. This is very important because it's challenging to compare the estimates of remote sensing and the estimates of national forest inventory plots over single pixels due to several limitations. For example, one of the main limitations when you think about forest species is that several times in a single pixel, you have, in truth, many different forest species. And to do that, we implemented this procedure. So we aggregated the remote sensing and national forest inventory statistics over these areas. And in this way, we were able to compare the outputs and the comparison, the agreement between remote sensing statistics and national forest inventory estimates was very large, was very good. This is the accuracy, the overall accuracy and the kappa coefficient accuracy we got when trying to predict coniferous versus broadleaves, and when we tried to predict the 7 species groups I was showing to you. So these 7 species groups. This is an image that shows for each cell the deviation between the remote sensing estimate, let's say statistic, and the national forest inventory or this Thompson estimate. And you can see that many cells are yellow, meaning that the estimate was very close to 0 very often. Here we have the same comparison between scatter plots, and you can see that the correlation was very good in several cases. A very important thing that you can see that this is shown also in the next slide is the number of plots. So the color shows the number of plots for each cell. So each point in this scatter plot is a cell, and the color shows the number of plots for this cell. And you can see that when you have forest species in which the cells you have not a lot of plots, you can see that the agreement between remote sensing and national forest inventory is lower, while when you have plots with a lot of when you have forest species with a lot of plots, you can see that the agreement is very large. For example, pines, you can see that there are a lot of cells with many plots, and the agreement between remote sensing and ground data is very consistent. This is showing the same. So you can see the deviation, and here you can see the number of plots. And you can see that when there are a lot of plots, the deviation is very small, so it's very close to 0. When the number of plots decrease, you can see that you can have also large deviation. A key point of integrating remote sensing with national forest inventory data is that in addition to map, you can obtain estimates. So you can obtain estimates of forest disturbance areas, you can obtain estimates of forest species coverage area, and you can obtain also estimates of map accuracy. So this means that in addition to the value, you can obtain also the confidence interval. This means that the accuracy of this map in this class was 73% plus or minus 2% with a confidence interval of 95%. Here we are showing just the the accuracy, but actually using a very similar method, you can calculate the interval confidence of the forest species area over the Netherlands in this case, but over a different country. As long as you can integrate the remote sensing maps that you predicted with the available national forest inventory data. So this is just to show that we implemented our own method, trying to make some step forward, but there are also other examples available, other very good examples available to do that. So to predict forest species using national forest inventory remote sensing data. And again, I think that this leads to my conclusions. So the integration of national forest inventories with remote sensing data holds great potential. So there are many applications that may be very useful. Many of them are also operational, so maybe implemented quite easily, and they're already available. But I think that a main issue is that remote sensing remains underexploited. So it's very rare to see official national forest inventory product exploiting also remote sensing data. And while I think that the way to go is to integrate, to try to exploit both of these source of information together to improve the forest monitoring in Europe. This is just a slide to tell you that about summer schools. I was listening at the previous presentation, and you were saying that summer school are a very good opportunity. So this is a summer school that we're organizing in Florence. This here, it will be the 4th edition. So we had already 3 editions in Florence. It is very nice to have students from the whole of Europe interested in learning more about Google Earth Engine. If you want to have more information, here it's my email. Otherwise, you can scan this, and it will be in the end of September. Thank you all for the attention.
Thank you for this nice introduction of me. Good morning, everyone. My name is Paweł Hawryło. I work at Department of Forest Resources Management at the Faculty of Forestry, University of Agriculture in Krakow. I think I am in comfort situation because colleagues Piotr and Saverio introduced you in general to applications of remote sensing in forestry in big scale, I would say, and I will focus on, let's say, simple use case. I will talk about modeling basal area increment in Poland, so in smaller scale. So first, what was the motivation for this study? As you may know, all forests know that this is one of the most important characteristics of forests in case of forest management, but also wildlife. Also, the previous studies which are available often use limited data sources because collection of this data is quite expensive and sometimes difficult to analyze it annually. Because in our team, we are working on also in implementations of this remote sensing data to practice, what is very important for what Krzysztof said at the beginning. And we are interested in identification of remote sensing derived metrics, characteristics, which might be useful for this kind of stuff. And we are also working in our team on modeling of mortality of different species in Poland. We have now a huge problem with not only with Norway spruce, but also with Scots pine. And having this annual data, we are trying to identify some meteorological or climatological characteristics which influence the growth inhibition of Scots pine. So just quickly remind what basal area is. So in my presentation, I am talking about stand basal area increment. So this, we can say that this is a cross-sectional area of all stands in the stand measured at breast height. And it's usually in Europe, it's expressed in square meters per hectare. So the input data for that was quite huge data set. It was collected under the project we are working on for it's financed by National Forests in Poland. We are developing the growth increment models, empirical models. And in this project, we established a network of actually 600 plots, but 300 of them are for Scots pine stands. Not pure Scots pine stand, but dominated by pine. They were stratified using age and site conditions to be sure that we are capturing the variability of different growth conditions. And they are circle plots varying in size depending on the age of the plot. The size is different because there is an assumption that we should have at least 30 trees per plot. So for younger stands, we don't need huge plots. But if you want to have 30 trees in old stands, sometimes the plot will be like 0.3 hectare. There are some such plots in the data. So the field campaign was done in 2022-23. Standard, let's say, 3 characteristics were collected, like DBH height, ground length, or species. Also the location of each tree. We have also the exact coordinates of plots and trees. And we collected the tree ring data from each tree on the plot, assuming that we should have at least 10 years of growth. It was assumption in the project. So finally, we collected more than 9,600 cores from these plots, and the tree ring width was measured in special software for that, of course, as usual. And then we calculated the DBH of each tree. It was updated based on tree ring width. Then we applied bark correction for that. Then summarized calculated basal area per tree and summarized for plots. You see the distribution of basal area increment, and increment was calculated as a difference between subsequent years. And then we identified, let's say, 3 groups of potential explanatory variables we want to use. One was ever laser scanning, the second was satellite images, Sentinel-2 and MODIS, and the next category was climate data or weather data, and we used TerraClimate for that. In case of ever laser scanning, we performed the data in LiDAR package for air, which most of you know if you work with LiDAR. We use some standard metrics like mean height of treetops. We use just simple methods for detection of treetops and used mean height of that. We calculated leaf area density, which is possible to do without any calibration to the field leaf area index, but we want to evaluate that. We calculated top height with the methods we developed, and we used also the site index models to calculate site index to know what are the growth conditions on each plot. And we also used this relative spacing index, which we have found very useful in our previous study, which describes the relative distance between trees. And you see some examples of different stands with different leaf area density and the view from the top of that. In the case of satellite data, we decided to use Sentinel-2. This is also why we were limited in time. Maybe I will just go back quickly. It's not here, sorry. We are using data since 2017 up to 2022, because since then we have dense time series of Sentinel-2 because the constellation was two satellites since then. So we are able to get dense time series. We used Google Earth Engine. Maybe a small comment here. Saverio mentioned the summer school about Google Earth Engine. Actually, the idea of using Google Earth Engine we got from Saverio team. I was there a few years ago, and I saw that it's very useful. And since that, we try to experiment with that. And I can recommend you to go in there for sure. It's very valuable to learn that, because you can easily and quickly calculate, as you can see here, for example, some vegetation indices for the plot, and you can see this time series for one selected plot for vegetation indices. There are more, about 15 vegetation indices we explored. There are some examples. Some of them are quite easy to calculate, but we also wanted to explore this quite new, let's say, index, which is plant phenology index. Vahid is here, was responsible to do that, to implement in Google Earth Engine. So from this all available data, Cloud 3 pixels, we calculated mean values for each month. In case of MODIS, we just wanted to use the one of the products from MODIS, which is photosynthetically active radiation. We know from different physiological growth models that this is important, that we wanted to add in our model, and we used average values for months. And finally, the climatological data, the weather data, was from Terra Climate, and we selected few metrics like climate, water deficit, drought severity index, precipitation, minimum and maximum temperature, and water pressure deficit. For modeling, we use generalized additive models. Since some time we use a lot of this method, we like this because it's, I think, quite efficient comparing to, let's say, fancy machine learning methods like random forest or super vector machine, something like that. But you can still have interpretability of your results, so you can analyze how these predictors, how the covariates influence your target variable. And this is very important for us because we don't want only to get the best prediction, we want to understand what's going on in our model and to check if everything is correct. We divided the data like 80% for training and 20% for testing. Additional context was to train on the data since 2017, 2020, but validate on different dates. So then we can also check if the model works on the weather conditions or spectral data, which was not used in the training data set. And we tested 4 models. Maybe the description of them is not the best, but I will explain what it means. We have the STAND model, which use only STAND data. Then will be ALS model, where we add average scanning metrics. Then is a climate model, which use this and this and this metrics. And finally spectral, which is actually full model. So spectral means we are using all of these data sets. There should be a better explanation, but I think it's maybe here it's clear. Here is an example of just a screenshot from R, and it's not important, the soft is not important here, but we have the list of finally selected variables. So in the STAND model, there was just a basal area and age. When from average scanning, we have 3 predictors, relative space index, slip area density, and site index, because the top height was used from LiDAR. The climatological data and the spectral. I don't have enough time to explain why these metrics are finally here. We started from simple correlation matrix, and we analyzed the variables one by one. And if, for example, you have 2 spectral indices which are highly correlated, like 0.9, so we selected the one which is more correlated with basal area increment, for example, and the same for different these climatological variables. There was a lot of testing. Maybe this is the drawback of GAMS, that you cannot just put 100 variables and get a model. You have to think more when you develop the model. And here are some results. So you see the validation on these 62 plots. It was actually 62, a random selection of variables of the plots. There were only 10 observations from 2022 because of the time of data collection. So most of them were from 2021. And what we observed is that we have important, I cannot show you, but you see that the improvement of the model, significant improvement of the model started when we added spectral data. You see that, for example, R² for stand, ALS, and climate is very similar. Also, the mean squared, root mean square or mean absolute error are very similar. But when we added this spectral data, the vegetation indices from Sentinel-2 each improved a lot. And it's also visible in the scatter plot, observed versus predicted values. This is the top, the bottom right plot. I think it's quite clear that is the best one. And then you can try to analyze the influence of the coverage of the predictor or on your target variable. So these are the so-called partial effect plots. So if you look on that, you can interpret that this is, for example, if you want to analyze the age, let's say you are looking on age, this shows us how age modifies the basal area increment, assuming that all other variables are kept at their mean value. So this is the standard, let's say, plot we use for interpretation of GAMS. This is why you have these values below 0. For example, for older stands, we have like -0.25. It means that if the stand has 100 years, the basal area increment will be lower of about 0.25 compared to the mean value. And thanks to that, you can look how different variables works. You can also look on interaction, because you can put to the model, as you saw here, for example, NDVI. You see that we don't have just a single NDVI from single month, but we have NDVI from April, June, and August. And using this formula, we are able to capture the influence of the NDVI from 3 months during the year. And we can observe this on such partial effect plots. On the right side, for example, you have similar situation for precipitation. You have precipitation from April on the X, from June Y, and these panels on the top of the panel, you have the value of precipitation in October. So you can see that the precipitation in April and June, what we could expect, is more important than in August, and higher the precipitation, we observed higher increment, basal area increment. But it's also interesting that if you have low precipitation in August, it can decrease the mean value of increment. Actually, the colors should be shifted, but it's the default. So maybe the red should be the decrease. Okay, I don't have time to spend more on that. We can discuss in the coffee break or later. But I just wanted to highlight that it's very useful because you can try to understand your model. You can even use something like adjusted predictions. So you don't have to use mean values of another predictor, but you want to, for example, check what are different differences between increment for stands with site index 15 meters and 35 meters. And with different NDVI. Let's say that NDVI in April is 0.2 and 0.8. And you want to compare how it influences your target variable. So I think it's very useful. So going to some summary or conclusions, the study is not finished, so I am here also to get feedback from you and maybe some suggestions, some inspiration. But until now, what we identified is that from airborne laser scanning data, the relative spacing index and site index were the most useful. The spectral data substantially improved our model. This spectral data was more important than climatic variables. And among these different tested vegetation indices, from red edge, shortwave infrared, the plant phenology index, finally our old NDVI was the best. The standard metric was the best here. And what is next? What we are going to do? What we plan? And also, I want to invite you from here to contact if you are interested in such topics. We can share the data. We can work together. Our plans are to evaluate, for example, how this ALS-derived basal area, the accuracy of that, will influence the predictions. It can be simply simulated because we will just add some error to basal area. For example, 50% on 20%. If we assume that from LiDAR we can get such accuracy, we can simulate the error and observe how it influences the basal area increment. We want to also develop separate models for TNET and anti-net stands. It was not done here because we just used all leaf trees, which were leaf in 2022. They will just drill core to get the data, but we have also the observations from the previous project, which was the field data was collected in 2015. So we will be able to also take into account the thinning and the mortality. We are now working on that to identify exactly what time each tree was removed or was dead. It will be also worth to check the cumulative values of vegetation indices and also meteorological data. We are preparing the data to test that. We want to extend the analysis to another regions and species. We have contact with colleagues from Czech Republic, for example. We are going to do that, and maybe another species as well. And the final step will be probably modeling on a single tree level, because it will be possible with this data, but we need to spend more time on preparation of the input.
Thank you, Piotr, for your excellent keynote speech, and Saverio for his overview on Google Earth Engine. So you basically told everything that I need to tell. And to save time, I could end my presentation here. But it's not so simple, so I will dig little bit deeper than that. So, as you told me that I am Janis Ivanovs. I'm representing Latvian State Forest Research Institute Silava, and I'm there for already 7 years, so quite a long time already. And my talk will be about influence of different forest tree species on the forest height predictions from ALS measurement, and also of different variables that are influencing ALS measurements. Yes. So, as we all know, ALS data can be used and is widely used to predict various forestry inventory variables. However, point cloud properties depends on various environmental parameters. such as phenology or different tree species or even different scanners that are used to make those ALS measurements. And we use ALS data in combination with NFI data to construct forest height predictions for 6 main tree species in Latvia, which are Norway spruce, Scots pine, birch, European aspen, grey alder, and black alder. So, as I told you, I used NFI data to construct those models, and shortly about Latvian NFI. So our NFI has started in 2004, and we have more than 16,000 permanent sample plots, which are visited in 5-year cycle. So, and we can get very good statistical data about forestry inventory variables, but there are little spatial coverage for the data. So we try to address it using remote sensing data. And our NFI sample plots are 500 square meters large or 12.62 meters in radius. So about ALS data in Latvia, first coverage of ALS data we got during 2013 to 2019, and 3 different companies were contracted to make measurements. So also 3 different scanners were used to make those measurements. And the idea for the data collection was simple: just do it in leaf-off conditions. So all data should be in leaf-off conditions in Latvia, but it is really one big lie, because it's usually not possible to get the data in that short period. So in reality, the data is collected throughout the year, except the winter period. So it starts maybe in early spring, goes throughout all the summer, and in some parts I noticed that the data is collected even during December period. So, and you can see those 3 different scanners used, like there was Beagle LMS Q780i. It was the best, like the most accurate of 3 scanners used, and it was used here by the border of Russia, because of they don't like that some surveying companies are doing surveys close to the border. And the rest area of the area was covered by Regal LMS Q600A and later LS70 HP scanner. So about conditions where data was collected. So you can see this map shows what vegetation period was at the time of data collection. So I split the data by week of the year. So spring and autumn data was considered as leaf-off data. Then in summer it was leaf-on period, and in the middle I decided to make it like between season data. So you can see that map shows that it was quite different coverage for whole country. And for 6 main tree species, you can see it's quite colorful map, and it shows like NFI sample plots and what tree species is dominant in that sample plot. So it's quite a challenge to make one full coverage on equal conditions for ALS measurements. about methods that we used to calculate metrics from ALS data points. So we used Fusion LDV software to cut ALS data according to boundaries of NFI sample plots, so radius of 12.62 meter. And in Latvia, our NFI sample plots are measured, like sample plot center are measured within 1 meter accuracy. So it should roughly represent the conditions of the NFI sample plot. And using the same software, we obtained statistics about vertical distribution of ALS points, such as various height percentiles, mean values, and etc. Then, to try to find out what are the influence of different tree species, different scanners, and different seasons on ALS measurements compared to ALS measurements, I used linear models and built those models on 25% of data and 75% of data, and 25% was left for validation, and metrics as root mean square error and mean average error were used to select the best models. So basically, I made those graphs for all the different combinations. For example, for each pine stand in each different vegetation season and for each different scanner. So I had more than a couple of thousand those graphs and then selected the best height percentiles in that case for each different condition. For example, in this graph, you can see the graph for Pinus sylvestris in on conditions. And from this graph, we looked at this root mean square error and mean average error to detect which height percentile gives us the best result for each condition. And then compare them in this graph to see is there statistical difference between the different conditions in those forest funds according to ALS measurements. And as you can see in this top box, there is universal model where all the data is just put in one box and model is like applied. And if you go deeper into different scanners, you can see that there is no significant difference between both Regal scanners, but there is significant difference between ALS scanner and both other scanners. So, and we can go deeper and deeper into different conditions. For example, is it coniferous or deciduous trees, or is it leaf off, leaf on, or transitional conditions? So, and the same goes for different tree species. For example, here I looked at Regal LMSQ 680i scanner, and there was significant difference for most tree species individual models comparing to all the data collected with Regal scanner. Only black alder in that case was not like significantly different from universal model. And the same goes for leaf off, leaf on, and transition periods. And the same graph goes for Leica ALS scanner. And those white boxes down below show that there was not enough data for building this model for this condition, and I should suggest that it's okay then to use like more universal model than more like detailed model. Yes, and then about what we can do afterwards, if we know that there is difference between different scanners and different conditions in forest when you do ALS measurements, then you should take into account those conditions when you predict forest height, for example, or different parameters from NFI. So yes, and then we built map for Latvia with where we predict different tree species, similar as Piotr already told us. So for first we wanted to find where the forests are, so we delineated it into 4 classes, like land use types: forest, agricultural land, water, or wetland. And there you can see the accuracy of the data. So we got forest areas with 96% of accuracy, and overall kappa score was 0.92. And we got this layer just using Sentinel-2 composites from 2021. I used 3 different periods: spring, summer, and autumn data, compiled all the data from those periods together, and calculated mean value from images without cloud coverage. So, and for tree species classification, I also used various metrics from ALS data, which were calculated, for example, depth water maps or wet area maps, which are available for us. And about wet area maps, William here will tell more about in next session, I think. Then also used normalized height map, which shows which areas in landscape are local hills and which are local valleys and everything in between. Also slope, elevation, and various other indices. And then I got this map. There is an example of those 6 main tree species in Latvia, and I also didn't want to predict main species for very, very young stands. So stands which are up to 10 years old were put in a class which is young growth forest. So it's very difficult to predict those attributes from Sentinel-2 imagery, which are 10-meter pixels. So yes, and you can see accuracy of all the different tree species predictions in the graph here. And yes, when we got the map of different tree species, we can apply forest height models to the map and ALS data, and basically build maps for various forestry inventory variables. Basically anything from NFI can be translated to the map. And yes. And conclusions for me that these different variables in conditions when ALS data is collected is quite important and should be taken into account. And the spatial data such as ALS and ground truth data such as NFI is useful to combine them together and get spatial coverage data. And starting from 2022, we are already getting second ALS coverage in Latvia, and I'm planning to build something similar as you did to predict some yield curves and for different variables. And for first ALS coverage, we got about minimum 4 points per square meter, and on the next coverage, we are getting 6 points per square meter. Yes. And dziękuję bardzo. Thank you for everyone for listening.
Okay, thank you very much. Markus, the mic is yours.
Thank you very much for the invitation and introduction. Yeah, like shifting the focus to regions, the third dimension becomes really important because regions are defined by vertical space. And yeah, maybe to put it in a simple question, today I want to address how can we use high resolution remote sensing data to assess impacts of urban vegetation. When talking about 3D remote sensing data, it's LiDAR data, what you see there, and also mixed up with aerial imagery you can see on the left. And yeah, one example what we try to do or what we are doing with this data is what you can see here. We have a digital twin with the trees integrated, and for the roofs of the buildings, the solar radiation model. Yeah. In my presentation today, I want to introduce background of my institute, why we deal with urban forests, give an overview about LiDAR data in Europe, explain a bit the workflow for urban forest mapping we use, and show some applications of the models. Yeah, I work at the Leibniz Institute of Ecological, Urban and Regional Development. It's a non-university research institute in Dresden, and it's highly interdisciplinary with, I think, 150 researchers working there, coming from 50 different disciplines. And our big aim is to research for the sustainable transformation of neighborhoods, cities, and regions. I myself have a background in geoinformatics, work in the research area spatial information and modeling, which deals a lot with spatial data and what you can do with it. The area itself has history in monitoring land use in Germany. For me, I'm specialized in 3D data, like 3D building models and the 3D tree models, which also form my PhD. One thing to mention is that at the moment we are setting up a research data center, and with that one, we are really committed to open data and open source. Everything that's why basically all the things I will show you today, you will hopefully find there soon. And yeah, it's all related that all applications are open source, so you can use them again. Urban forests. When talking about urban forests, we really mean all trees in urban and peri-urban areas. That means we really have forest stands, but also trees in parks or individual street trees, and also trees on private property. And yeah, I don't think I need to talk about the importance of that. They're really critical for future. And that's why also a lot of goals and objectives of about trees are anchored in different political and legal instruments. For example, probably coming this year, the EU Nature Restoration Law, where it says that there should not be any loss of urban green space by 2030, which means there will be a lot of pressure on urban space because we also need new housing, we need anything else. So it's a real trade-off if you can keep the trees or have to build a new house. Yeah, and that's why, for example, mechanisms like the system of environmental economic accounting are important. And that's why it's also so important to have objectives and indicators linked that you can measure what is happening. Yeah. And that all needs a high resolution databases, and that's the motivation why we deal with such models in urban, in urban areas. Yeah, glimpse overview about open data availability in Europe. We already heard there's a lot of LiDAR stuff going on, and more countries have full coverage of their country or partial coverage. Yeah, if you miss your country on that map, it could also be that I didn't find it on the internet because it was with the language barrier sometimes a bit difficult. But yeah, I think it's obvious that there's more and more LiDAR data coming. And also, for example, Spain on the map is still without point out with 4 points, but they have a lower resolution point out of and flying at the moment new programs. So yeah, LiDAR data is there and we can use it, I think. And if you have LiDAR data, you can do cool stuff like I found on the Polish geoportal, the 3D tree model. Yeah, which is something similar to what we do. And yeah, I am happy to present now how we process such models from LiDAR data. important to say about our workflow is that we lay focus on regional scale modeling so that you can process entire areas like, for example, Berlin or Amsterdam, like in quite short processing times, because dealing with 3D data processing can be really a problem. Yeah, and it covers also the whole workflow from classifying the point cloud, which is, yeah, there are a lot of buildings and other stuff we need next to the trees. They're classifying the trees in the point cloud, then segmenting individual trees, and then reconstructing them parameterized. And today I will lay focus on the first part because, yeah, that's where we have most influence, because tree segmentation is already always a challenge, and there are a lot of errors coming anyway. Yeah, again, overview of the input data. We have the LiDAR point cloud. We need densities around 4 meters to produce 3 models. The lower resolution point clouds, it's too much space between the individual points. The 3D building model and aerial imagery, which is important to have. The near infrared information to calculate the NDVI. Yeah, and the first step we do is classifying roofs in the point cloud, because yeah, buildings are really dominant. That's why we use the 3D building models that are already there anyway. It's the points you see classified in yellow. Then we also calculate all coplanar points, like looking which points lie on a plane. There's one small red roof in the front of the image, maybe you can see it. That's stuff that's not in the building model, but we can detect like that. And if you filter the building points out of the point cloud, yeah, you see there's a lot of trees, but also a lot of other stuff still there. Yeah, and that's where we take it to the next step and rasterize it. Here we stay in the point cloud because it can happen that trees overhang a building. That's why we want to do that in the third dimension. Yeah, but for the next step, we go to raster level, rasterize it with cell size of 0.5 meters. Yeah, have a digital surface model then. That's not yet quite a canopy height model, but we are on the way to getting there. And yeah, for this surface model, we apply watershed segmentation to form objects that mainly or somehow approximate tree grounds. We use the watershed segmentation to do object-based image analysis, because if you want to classify on a pixel-wise level, it will get way too noisy. And with the watershed segments, although the tree grounds are not completely correct, but you have objects that are somehow meaningful. And for each tree ground, we can then calculate features like the mean number of returns, because if a laser pulse hits a tree, it will have multiple returns. If it hits a building or a street or anything else, it will just be returned as 1. The mean NDVI, the compactness of the segment weighted by segment size, as usually tree grounds are more or less round, while other segments could be longer shape. And what we still have included there, but we don't use it that much anymore, was the difference between the first and the last pulse, because it could help to differ between coniferous and deciduous tree species. But as the segmentation is too noisy in individual tree grounds, we also get errors with that. So we don't really use it anymore. But what you can see is on the bottom right picture, like our site, we really get a quite clean classification of tree grounds, which we then can put back to the original point cloud, have the 3 points isolated in the point cloud. And then if we would rasterize it, we would have the canopy height model for areas. Yeah, and based on that classification, we can then detect individual tree grounds and segment them. Therefore, we use a classic local maxima filter with variable window size. Yeah, but as I mentioned, there are always some errors. I think we calculated some numbers based on the official tree cadastre runs for 1,000 trees, and it was like on street trees, which are mainly isolated and don't mix up that much with the grounds, we achieve accuracies around 70%. But if you look to urban parks, the accuracy decreases to around 50%. but still we can segment into 3 grounds, and we laid focus on the geometry more than to capture the volumes. That's why for each segment then we fit into it an ellipsoid, not a circle or a ball. So we can adapt to the different ground shapes you get from segmentation. And yeah, then put it into city GML format as really 3D geometries. Yeah, so that's what we get then from our workflow. We have mainly 3 products: the canopy height model on the bottom left, individual tree positions in the bottom middle, like with geometric features like the height of the trees, ground, volume, ground dimensions, and the 3D tree model. We use this for small scale indicators like green volume, canopy coverage. We integrate the trees in 3D shading simulations or modeling of the urban climate. That's some examples I want to give you now. First one is the urban green volume. You see the city of Dresden in Germany, and for each building block, we can just assess the green volume. And yeah, we did this together with the city of Dresden, with the administration there, because for them it's important to see where is enough, maybe enough green, where isn't enough green, and which areas have risk of facing urban heat islands or not enough green for their residents. Also, it's not the first time we did it for Dresden. We had it with another LiDAR flight from 2009, which had other parameters, like it was mentioned before. If you compare LiDAR point clouds, they all have some specifications, and yeah, you can't compare them 1-to-1, but still you get an impression of where trees were growing, of where trees were cut. Yeah. Next one was, that was initially how we started to deal with the urban green models, because we had a project where we wanted to assess the solar potential on buildings. And we thought, okay, if we, especially for building integrated photovoltaics, which means also on the facades. And we thought, okay, for that, we need to consider the shadow of the trees. And that's how we started with all the tree topic. Yeah. So we built up the model with the buildings, the trees, and terrain, and then you can see how the modeling works. On the left is buildings and trees. Then we put a point grid with 2 meters resolution. So each 2 meters was a point, and modeled incoming solar radiation for each of the points. And on the right side, you can really see on the facades where the trees cast the shadow. We used it for the solar radiation, but you can also turn it around and say, like, where trees shade the building, the residents are a little bit safer against heat and anything else. Another application was assessing local climate regulation. It's for the city of Munich. Again, we have 2 time series. On the picture, you see the area around the English Garden. And for each, again, on building blocks, we calculate the cooling capacity score, which considers the tree heights, but also like buildings, how many people live there, and the land use as well. And just through integrating the different tree heights, you can see where the tree grew, where the cooling capacity got higher, or where trees were removed because a new building came in and the score reduced. And as a last application, that's also a nice project, where we fed all the data into a big AI model. And the AI model is mainly based on the sensors you see on the left picture. Throughout the city, there were, I think, 500, the city of Dresden again, 500 such sensors placed, which measure the air temperature. And then we can combine it with structure, traffic, weather and climate data, and the tree heights. And first of all, through measuring the temperature all the day and all the year, we see where it's getting hot and not. But through also having all the other data in, we can plan like what happens if a new water is planned if the trees are removed, but buildings come in instead, and then simulate how it will affect the heat. Yeah, that was overview for me. If you have any questions, feel free to ask them now, and yeah, you can always contact me under the email you receive.
The floor is yours. Yeah, thanks for the introduction. Thanks, Markus, for the really nice analysis. I will try to connect to this topic. Yeah, and my topic today is modeling vegetation indicators in urban areas with Sentinel-2 and high-resolution reference data based on a deep learning model. So it's another scale. It's kind of a Germany-wide scale. So how did I structure my presentation? First, I will talk, or first I will give a small introduction. And the second point will be the high resolution reference data. Then I will talk about the Sentinel-2 modeling. And at the end, I will give some small outlook and what are the next steps. So introduction. And the whole study is actually embedded within the project Urban Eye. Urban Eye, the project that started in the January of 2022 and goes until the end of next year. There are 3 different project partners, Luftbild und Planung GmbH, a small company in Germany that I'm looking for, then the city Leipzig and the Technical University Berlin. But there are also a lot of other cities involved in this project, about, I guess, 25 or 30 cities, is spread all over Germany. And yeah, the whole project is funded by the BND. So what is it actually all about? Within the project, we want to develop Germany-wide indicators for cities, so that they can actually monitor their climate adaptation management. And we are going for a lot of different indicators, but in this presentation and in my study, I mainly focus on the green volume. So what data actually should be used to model the green volume? And we are focusing on 2 different kind of data sets, Sentinel-2, so satellite images and aerial images. And yeah, they both have their advantages and disadvantages. So aerial images on the one side, they have a really high spatial resolution, up to 20 centimeters, which is actually pretty good, especially for urban content, for the small details. And a lot of times, there's also some height data that is actually crucial to kind of model green volume. And sometimes it comes from the same flight, sometimes from a separate laser scanning flight, but aerial images also have some downsides. As we have already heard earlier, in Germany, they are not freely available from all over the country, and they are not open data. And the acquisition times, actually, we get an image maybe every 2 to 3 years. And even then, sometimes we are not getting an image from a summer flight, so it's hard to do some vegetation analysis with this. Sentinel-2 data on the other side, we have the Germany-wide coverage, and it's open data, and it has a really high temporal resolution. Even if we don't have a scene without clouds every 5 days, but we have multiple scenes within a year, so we have some kind of like a time series. And the spatial resolution, as you can see, it's not that good. It's aerial images, it's just up to 10 meters. But you can see it's kind of enough to see some small details in the urban context. So how to actually combine the best of both worlds. Therefore, we developed some kind of like a workflow. So our idea is to collect some kind of high resolution vegetation height maps on aerial image level. And then we use those vegetation height maps, scale them up to different indicators, like, for example, for tree coverage or for green volume. And then we train a satellite image time series classification model to predict or to roll out the indicators for the whole of Germany and for multiple years. But yeah, of course, the prediction then relies just on spectral data without any height data. So we definitely have to ask us 2 questions. How does the model actually perform on independent areas? Because at the end, then the model is just trained on specific spots in Germany. And we have to find out how good the model is on independent areas that the model has never seen. And we have to ask us the question, how does the model perform on independent years? Because the best case would be we have a really great generalized model that can actually also predict the future years, so the next years maybe, yeah, would be the ideal case. But let's have a look how this works. So let's go to the high resolution reference data. Yeah, so the idea is actually that we have an aerial images and we have some height maps, normalized digital surface model. And at the end, what we have to do to get some vegetation height maps is simply just filtering out the buildings, the bridges, and maybe give some constant values to areas that change in time, like cropland or grassland. And to do this, we can actually use some rule-based approach. So we collect a lot of data and try to filtering out the stuff. But we also help ourselves and we developed some kind of like unit models that does this for us so that we can get some vegetation height maps from aerial images and the height maps. And what we have at the end is we have high resolution reference data sets from 20 cities spread all over Germany from 5 different continuous years. To actually validate this kind of data set, we rigidly interpreted 1,000 points per city, and that yeah, that this point is no vegetation, or this point is grassland, or agriculture or vegetation. And then we just had a look, what does our vegetation height maps say about those points? And we can see that it's actually pretty all right, pretty good, because the values are as assumed. But we have to take care, of course, because here we're taking the median. The median doesn't consider any outliers. But we can see that in general, the points are on the right spot. And if we have a look at the standard deviation next to it, the standard deviation is more outlier sensitive, then we will see that there are some outliers in the vegetation height maps. And it's mainly that the model didn't get to filter out the borders of the buildings, so that the building borders are still maybe in the vegetation height maps. But overall, it's a really great reference data set, so we can continue with the upscaling to satellite level. So if we upscale the vegetation height maps to an indicator like green volume, it's actually that with the vegetation height maps, we have the cubic meters for the pixel, and we then just sum it up for the sentinel pixel. So we have the sum of green volume within the sentinel pixel. And therefore, or yeah, for the whole modeling Sentinel-2 level part, we are using a force data cube, yeah, developed by David Franz. It's actually pretty good for the urban content, especially because the sentinel scenes are co-registered to each other. And yeah, and we have a fixed homogeneous extent for the satellite analysis. So now I rushed a bit over the first 2 points because I want to actually focus more on the Sentinel-2 modeling. So how did we do that? Yeah, first of all, we now have the upscaled green volume reference data, and we now need to actually sample down some points to train the model and to validate the model. And how did we sample the points? We stratified the sample points by green volume and by tree coverage, so that the model can actually learn from equally distributed response variables. And we set a minimum distance from the points of 30 meters, so that we can kind of minimize the spatial autocorrelation. And at the end, after step 2, we have this amount of reference data. So we have about 2.5 million, but as you can also see in Berlin, for example, we have about 400,000 reference points. And on a smaller city like Saalfeld, we just have 20,000 points. So we don't want this uneven distributed amount of sample points. And as you can also see, 2019, for example, we just have 2 cities. So we kind of equalize the sample points temporarily. So we have every year we have the same amount of reference points, and then on the same way, the distribution between the cities also kind of equalized. At the end, we have about 900,000 reference points that we now can use to train our model, our Sentinel-2 model. So how did we do that? Yeah, so for the whole modeling part, we used a 3 years time series from 10 Sentinel-2 bands. So 3 years just means that if we want to model the green volume for 2019, for example, we take this time series from 2016 to 2019. And as a model, we take a transformer encoder architecture that can actually handle some irregular time series so that we can use the raw spectral data and don't have to interpolate or aggregate the spectral values. And then what we also did is some hyperparameter tuning that we can, that we have a look what model parameters work best to model this specific case. And related to the research questions now of the generalization of the model, we then also included some regularization strategies. One was that we added a two-side positional encoding, so that the day of the year, the timestamp, is not just encoded on the continuous manner, it's also encoded on the periodically pattern, so that the model actually can learn, okay, the spectral value in the April of the first year can look similar to the spectral value of April of the second year, but the model can learns also that these are actually two different years. Another thing that we added is some time series augmentation, and therefore we use some day shifting and annual scaling, so to go for the different in start, end, and peak of the phenological season. And we also did some zeroing out. So we zeroed out some spectral values from the time series so that the model can actually learn to handle differently dense time series. So, okay, now we got the model, and now we can easily just put in all the reference data that we have, split it in 70% training, 20% choosing the model, and 10% testing the model. And we get some nice accuracies like here, 0.86 R², sounds pretty good, but it doesn't tell us anything about how the model performs on independent areas and on independent years. So to answer this question, especially for the how does the model perform on spatial independent areas, we actually have to keep the temporal bias at a minimum. So we just had a look or compared results from within 1 year. We took 2020 because the cities are actually nicely spread, and we have a lot of cities within this year. And then we hold back one city like Berlin, for example, train with all the other reference points, and then we are predicting Berlin. And we're doing this for every single city within this year 2020. And what did we get? At the end, we get, without the regularization strategy, we got those accuracies. As you remember, with the really general model, we have some accuracies, or the general validation, we got some accuracies from 0.86 R². And as you can see, the accuracy just went down. So the spatial independency definitely has some influence on the model results. And especially in Dresden, as you can see here, the R² is at 0.7, and the root mean square error is actually really high. So why is this? If you have a look at the map, you can see that Dresden is actually really isolated in the eastern part of Germany, and the other cities somehow have some other cities that are next to it. So maybe the model already can learn from other cities how the spectral and proper patterns are in this region. Just an example. And then we just applied regularization strategies, and we, sadly, we cannot see much. So it didn't help really much with this specific case. And the accuracy sometimes went a bit up on Gießen, so it got better. But sometimes in Dresden, for example, it even gets worse. So for this case, the regularization strategies didn't help that much. So let's have a look on the other case. How does the model perform on independent years? Therefore, it's a bit more tricky because if we have a look at this, we actually have to fix the spatial domain and reduce the spatial bias. And as you can see with our reference data, we just have 2 cities where we have the reference data from 2 different years. So it's hard to actually fix the spatial domain. So we did for our project partner Leipzig, and we just manually mapped some points for different classes, 100 invariant points. So this means that we can be sure that within those 5 years, nothing happened in those 5 years within this point. Of course, so we don't consider in this case that the vegetation is growing in the 5 years. This is kind of an assumption. But then if we have those invariant points, we can say that, we can take a reference from Leipzig from 2018 and just roll it out in all the other years. So we know that for those points, we have a reference for all the 5 years from Leipzig. And the invariant points we actually mapped with web map service, with Google Earth for some satellite data. So we just took points where we are definitely sure that nothing changed over those 5 years. And then we actually did the same. So then we have the reference for 5 years, and we're holding back 1 year. So we hold back the reference data for all the year 2018, and then predicting Leipzig for 2018, then holding back 2019, predicting the year 2019 for Leipzig, and so on. And then we had a look. So yeah, as you can see here now, the plots, and the upper plot is for the class medium vegetation. The lower plot is for tall vegetation, and the red dotted line is actually the mean of the reference value, and the green line is the mean for the predicted value. And as you can see, the medium vegetation actually kind of gets over predicted or overestimated. The taller vegetation gets underestimated, but you can also see that there's a lot of noise within the model, and it's hard to actually monitor with this result at the moment, because yeah, I mean, as you can see, the model predicts 2020 the medium vegetation much higher. And if the city then says, oh, our green volume increased, but it's just because of the temporal bias, it's actually not that good. But on the second side, we applied the regularization strategies. As you can see, the model prediction actually gets much better. We don't have the high uncertainty for 2020 anymore. We got a bit smoother prediction, and this results also we can find in this table. So we can see that for all the classes that we divide, the root mean square error actually got decreased, except some specific situations, especially for medium and tall vegetation. The regularization strategies really help. For example, here, the 2020 medium vegetation, the root mean square error gets halved. So it's actually, so regularization work for the temporal generalization really good. But we definitely have to consider that those are just 100 invariant points, so just 100 reference points per class. So it's not that much. So we have to take care of this one. Yeah, so that's about my first results. Now let's go to the outlook and to the next steps. How can we improve the model even more? So especially for the spatial content. If we want to talk about generalization of models, we definitely have to talk about foundation models. Foundation models are some large pre-trained models, sometimes self-supervised, that gathered a lot of general information about different areas and different temporal stuff. And those general models, those foundation models, can then just be fine-tuned with some specific high-resolution reference data. And there are two models that I want to mention, and that two models that I want to mention that were developed last year that are actually really promising. It's a quick time model developed by IBM and NASA, and the Presto model. Besides the foundation models, and there are also other papers that kind of try to encode the coordinates so that the model knows exactly if it's predicting or training where it is at the moment. And then there's another paper that also trying to add some terminal positional encoding instead of some calendar time, day of the year encoding. It completely makes sense actually, because it is a better indicator for the start, end, and peak of the season and some variation than the day of the year, the calendar time. So the terminal positional encoding is actually the summed up temperature within the year. Besides this, can also do some further analysis. We can, or we do some analysis for the tree cover density. So how is the tree coverage? Then we can also have a look, how does a pixel heterogeneity influence the model, especially relevant for urban context. We can go for some accuracies for aggregated areas, like you can see here on the right side. Maybe the uncertainty isn't that high anymore if we aggregate the results to some areas within the city, and we combine some indicators, different indicators together, even with socio-demographic data. So that's it. Thank you for your attention, and feel free to go in discussion also in the lunch break now with me. I would really be looking forward to this. And one last thing, we fully support open science. So the data will be available after the publication, and the code is already available. But yeah, be gentle, because the code is not that good documented yet, but it will be, and maybe there will also be a Docker image or something. Thank you. Thank you.
So I'm from Slovenian Forestry Institute, but the last 2 years I spent in Germany and Technical University of Munich, and I will be presenting you what I was doing. And as you can see, this is not only my work, but there is a lot of people who contributed, and I would of course like to thank everyone. So we will mainly talk about forest growth maps. And I think we can all agree that forest growth is very important. Yeah, so it's a proxy for net primary production. It's important for forest owners to see how much they can earn. So forest growth, I think I don't need to spend time of convincing you that it's really, really important. And already more than 10 years ago, there were these, I would say maybe not the first maps, but really comprehensive maps about the forest growth, which nicely show the spatial distribution of how forests grow in Europe. But what I miss here is the temporal resolution. So we know that forests and trees do not grow every year the same, but we also have variability in time. And here we come to the tree rings. And I include this slide because I'm sure that not everyone here is from forest community. And trees in temperate zone, they grow on every year they produce one ring. And as you can see already from the macroscopic perspective, rings are not the same every year. So there is huge variability, and this variability also drives the temporal variability of tree growth. So if we measure tree rings, we usually get something like that. This is only a small section, but as you can see, rings can be very narrow, tree rings can be very wide, and this is something that we wanted to incorporate into modeling. We are not the first one who tried to create maps of forest growth based on tree rings. A few years ago, there was a study by Bodesheim, who established annual maps of species growth on European land. This is very nice, but what we wanted to do here is to add remote sensing, because these maps are based only on climate, and we know that climate is an important driver, but it's not the only driver. And by remote sensing, we approximated forest conditions, soil conditions, so sand conditions, and as we will see later, this really worked well. Okay, so tree rings and remote sensing, it's not something new. Here I show some studies already from 20 years ago where they linked, so NDVI, for example, and annual increments. So this shows us that it's really promising to combine remote sensing, climate, and also some other data to create maps of annual tree growth. So this is our main research area. But we need data. So, and this is often not easy. And I spent more than 6 months contacting people, convincing people to contribute this data. And we then ended up with more than 700 sites from Central and Eastern Europe, which was our ground truth data. So we had enough data for 8 main tree species. And then we also built models which combined different species. So we ended up with so-called forest-type models. To do so, we used Greenland cover. So we classified each site into broadleaves, conifers, and mixed forests. Okay, so we used high-resolution climate data, EOPS data. We created many variables related to temperature. So we aggregated into seasons. So we had spring temperature, summer temperature, growing season temperature, the same for precipitation and for water balance. Then we extracted for each site, we extracted the remote sensing data, Sentinel-1. So this is remote sensing conference. So I probably don't need to spend a lot of time on what Sentinel-1 is. So basically, we calculated the so-called radar vegetation index, which is sensitive to biomass. So the higher the radar vegetation index, the higher the biomass, which again reflects something into the forest. We use Sentinel-2. We focused on 4 different vegetation indices: NDVI, EVI, NDRA, and NDMI. So I know there are a lot of different indices, but we already at the beginning, we said, okay, let's focus here because we have photosynthetic activity, we have moisture, we have vegetation. And we also use the digital elevation model because we know trees in higher elevation, they grow, they shorter growing seasons. In general, we get narrower tree rings. Okay, briefly about modeling approach. We heard something about random forests already today. So we compared and tested different machine learning methods, but random forest was simply the best. So what we evaluated different methods in terms of cross-validation, and then we said, okay, random forest is the way to go. Other algorithms were also artificial neural networks, support vector machines, also mixed models. We started with the linear models. And for us, random forest was the best. Although I could say it's not really so big difference between, for example, neural networks and random. So as I said, we have 8 species-specific models. Then we have 3 forest-type models and 1 general model where we just combine all the data. But as you will see, this doesn't really work because the models are better if they are more specific. All evaluation, so all the statistical metrics which I will show are based on independent data. So we use the spatially blocked. So this is really important. We did not randomize the data. We kept the time and space as structured. Because if you randomize the data, you get better results. So I think we know that. So we kept fixed the blocks. And then evaluated different models in terms of test data, so the data that was not used for the training. We also used one approach which I'm a really big fan. So this is so-called area of applicability, and this basically tells you whether you have enough data to predict for certain things. So if you have data from Poland, you probably can't predict growth for Italy, but maybe you can do it for Czech Republic. You're not so far away. So we use this. I will explain later what is the application. But okay, we can now take a look at the results. So in terms of cross-validation on independent data, the best models explained around 50% of variance, and these were species-specific models. For example, Quercus robur, Quercus petrea, these models really worked well. When we had more data, for example, when we combined Fagus sylvatica from Lithuania, from Bulgaria, from Slovenia, we had only one model. And as you can see, in this case, we were able to get approximately 25%. But now, after this is already published, I started to think that, of course, it would make sense for the species where we have enough data to make regional models, so that we don't have the same independent variables for south and north, but we should probably go deeper into this. When we combined different species, it worked relatively well for conifers and for broadleaves. We had about 20% of explained variance, but it didn't really work well for mixed forests, because in mixed forests we have surface reflectance for different species, but we have chronology only for one species. So this is not the way to go, but this is more like a proof of concept. One of the questions which we asked is how much remote sensing actually adds to climate. And the answer was on average 5%. So we trained all the models using only climate and elevation. And then we repeated the procedure, adding also remote sensing. And yeah, on average, the increase in explained variance was 5%. In some cases, it was higher, for example, up to 11%. Then we established the so-called partial dependence plots, as we have seen today before, because many people say, yeah, that it's machine learning, you don't really know what's going on behind. But we can really see that the effects of independence variables are expected, and I was very happy to see that with increasing photosynthetic activity, we also get wider rings. With increasing moisture, we also get wider rings. And yeah, this is, I think this brings a lot of confidence into our models. Similar approach also for the SAR data. So with higher radar vegetation index, we also got higher growth. Okay, so these are our maps. This is our final product. So we at the end we combined forest type models. So we have 3 forest type models. Below it's Greenland cover classification, and we made predictions for our extended area. So Central, Eastern Europe, some Scandinavia, Balkan, and yeah. So I'm very happy how this looks like, although it may be a bit confusing at the beginning, but we can really see that the higher growth rates are in regions where we know the trees grow more. For example, Slavonia in Croatia, then in Eastern Romania. But the more we go to the north, so the shorter the growing seasons, we get narrower tree rings. So I know there's still a lot that can be improved in this, but for the first try, I think it's good. So about the black pixels. So black pixels are the pixels where we don't have data that support the prediction. So these are the pixels outside our applicability range. You will see in the next slide what's going on. So we compared distribution of independent variables within and outside this area, and we can clearly see, for example, for the conifers, that pixels where we don't have enough data for the predictions have in general lower NDMI, they have lower NDRA. So there is systematic difference between this, which means that in the future, if we really want to make these maps reliable, we have to go and sample this data, right? So if I go one back, the black pixels are mostly in Italy. We have barely maybe 2 chronologies from Italy, from the Balkan, and in the Alps. Yeah. So because also when we started our project, we called it lowland. Yeah, how it was called MEOS. So yeah, without high elevation areas. So for the future, I hope we will have time and we will have the capacity to do it. We will go and collect the data in these regions, and then I think that these maps can really be useful tool for different reasons. Because why do you think we need these maps? For example, we know that drought is really problematic. Now in last 10 years, we get extreme droughts every 2-3 years. And if we have such maps, we can clearly assess the impact of droughts on the forest on annual level, and we can see which species are more vulnerable, which species don't react. And I think it would be really great to have such products available. Okay, so I will stop here. You can access the publication, and if you have any questions, I would be happy to answer. Thank you.
First of all, thank you for the invitation. It's very pleasant to come here. In my village that I left yesterday, we still have snow. So it's a nice change to come to summer. I work at the Swedish University of Agricultural Science. I'm located in northern Sweden. And today I'm going to talk about how to map wet areas in the forests. I have split this presentation up into first a little background about Sweden, since you're Sweden. A little bit about LiDAR, some topographical modeling, some machine learning, and then finally some soil imagery. So if we start with the geography of Sweden, this is one of my favorite maps. It shows the population density of Sweden. So each one of these bars is more population. And you can immediately see that most of the people in Sweden, they live in the south. And if we have a look at the land use map, it's mostly forests, especially in the north. And over the last 30 years or so, the trend has been that people move away from the forests and out to the coast and into the cities. This is a global trend, so it's not just specific to Sweden. But this means that we have a handful of people left managing the majority of the land in Sweden, the forest. And to do this, we're using extremely big and heavy machinery, and they're very efficient. Sweden has about 10% of the wood export, even though we are a really small country. So the forestry in Sweden is quite intensively managed. We have a lot of automation. One of the problem here is that since so few people are managing so much, they have to use maps for remote sensing. So this is a figure of the water quality issues in Swedish forests. It's going to be in 3 colors, where red is bad, green is good, and then 3 scales. So the inner circle is local scale, then we have landscape, and then finally national scale, which is in water terms the Baltic Sea. And we can immediately see that, okay, we have some major issues with water quality in Sweden regarding mercury and sediments on the local and regional scale. This is the same figure, but it shows the parts that forestry is responsible for. So forestry is mainly responsible for sediments, nutrients, and changes in runoff. And one of the big reasons for this is the damage from heavy forestry machinery that moves across the landscape. And if you drive in a wet area with a 30-ton machine, you will create these ruts. And this rut will in turn have some side effects. For example, you compact the soil itself, which reduces the forest production in that area. You change the hydrology, so you might even create new streams or new paths for the streams. We have erosion. Sediment ends up into the stream, covering habitats for the stream. And we have nutrients that leads always out to the Baltic Sea and causes eutrophication. This is all things we want to avoid. But this is a problem. There are too many trees in the way. Traditional maps are drawn from aerial photographs, and from aerial photographs you can't really see what's beneath the canopy cover, which means that we have very little idea or very little information on what's underneath the forests. 60% of all wetlands in Sweden are just missing from the map. 80% of all the streams are missing from the map. And it's really hard to plan forestry operations with heavy machinery when you don't know where streams are. But then we have the first solution is LiDAR. You already know what it is. You fly with an aircraft, shoot some lasers, and count the time for the lasers to come back to the aircraft. And then the trees are mostly in the way for you. I'm a soil scientist. So if you only look at the ground returns, then you can remove all the trees and get a high resolution digital elevation model. So we have this for the entire country. This resolution is 2 by 2 meter. We have a new one, which is pushing 0.5 meter resolution, but for this project, I used the 2 meter one. And from this high resolution digital elevation model, we can start to model things. The very basic thing to do is just pour some digital water on the digital elevation model and see where water accumulates in the landscape. And where enough water accumulates on one point, it goes from being groundwater to being surface water in the shape of stream. However, we also have a lot of roads in Sweden. And if you look at the LiDAR scan is from above, and then you can't see what's a bridge or where the road curves are. So when you try to model water, it ends up just stopping there. You create a dam. So my first project was to remove, to locate the current locations and then carve a path with the digital elevation model. So I have some examples. This is a stream, the original model. If you apply the traditional low-gravity model, you just end up with a flooded area and you lose some information upstream. But if you instead reach the channel across the road, you retain information above and you get more accurate stream level. So we did this for all of Sweden. But the next problem is, okay, we want to have buffer zones around streams. The traditional way to do it is just have a 10-meter something fixed buffer. But we want to have more dynamic buffer. To do this, we applied a method called topographic depth to water. It was developed in Canada, and it looks at the surrounding terrain near your stream. And if the area is flat, it's more likely to be wet, and if it's steep slope, it's more likely to be dry. The problem with Sweden as well is that we have different seasons. We have winter, and during spring the snow melts, and it's wet everywhere. And during the summer, we get different patterns. And then my task was to upscale this for the entire country of Sweden. And we have large differences in Sweden depending on where you are. So that's where machine learning comes in. And the basic principle of machine learning is to, instead of programming the model by hand with code, you program it with data. And there are a few different ways to do this. You already heard of random forest, for example. It's a decision tree based method. I chose to use a slightly upgraded method. It builds on random forest. It's called extreme gradient boosting. But instead of building all the trees independently, you build the trees one after the other, and the following trees are trying to correct for the errors by the first tree. So for example, if you have some, let's say this is the Canadian flag, and this is our national forest inventory of the Canadian flag. So the first tree will find the big patterns in the data. There's something white in the middle, something red on the sides. The following trees will try to correct for the errors by the first one. There should be something red there as well. And then you build more and more trees until you get a model that sort of represents the reality. So this is the method I use to model soil moisture. This is the Swedish property map. It's the best map we have for Sweden today. It's made from aerial photographs, and it doesn't contain a lot of information. You have some streams in the center. There is some wet areas up in the upper part of the image. And the reason for it is, again, all the trees are in the way. So first we remove the trees. We applied some depth to water. This worked quite well, actually. The problem is that we have so much variability in Sweden. So if you try to apply that one model for the entire country, it doesn't really work. So this is, for example, 30 years average runoff in Sweden. And the northern part is a lot drier in the winter because it's frozen. And the southwestern part is very wet during the winter. In the spring, we get different patterns. And in the summer, we also get different patterns. So depending on when you're there and where you are, you have different moisture conditions. I also took soil information from the Swedish Geological Survey. So these are quaternary deposits. We have estimated soil depth as well. So the distance from the soil surface down to the bedrock. And from the digital elevation model, of course, we use the elevation itself, but we also modeled like 30 different topographical indices from this elevation data. So depth to water, topographic wetness index, roughness, slope, aspect, all of these traditional topographical indices. And then we also included all the peatlands, because open peatlands are quite easy to see from aerial photographs. So we included them as well. And we had calculated both microtopography, that's the topography difference within like 30 meters from you, but also macro topography, which would be the topography of on a landscape scale, so mountains, valleys, rivers. We used different scales. So the original DM was 2-meter resolution, but we also aggregated it to 8, 16, 24, 38 meter as well to get different scales. And this is our view and the 5 data of Sweden. And we have estimated soil moisture based on vegetation and location in the landscape. So this reflects the average soil moisture conditions during the vegetation period. That's the training data. So I used 80% of it for training, 20% for testing. So this is an animation showing how the random forest or the extreme gain boosting model is learning. So in the beginning, the model is quite bad, but then you add more and more trees and it corrects the mistake. And in the end, you get a pretty good model. So in this map, the colors are not that good, but red is a high soil moisture content. That's where you don't want to drive heavy machinery. And green is the drier areas. And the most interesting areas is in between, the yellow, because those are the areas that get swept during the snow melt, for example. So that's where you have this transition from groundwater to surface water. And that's where all the fun geochemical things happen. So we have created this, we call it the SLU soil moisture map, because SLU made it. We have implemented it for all of Sweden. It's available for free for all the forest companies, all the other agencies. And according to the forest industry, this is the best thing that has happened since catch-up. That's a good job. So if you have some metrics, the original map that we had before has a kappa value of 0.39. The static depth to water map was a lot better, had a kappa value of 0.56. But this new soil moisture map has a kappa value of almost 0.7. And something that's really interesting is now I combine both traditional maps like soil, the coordinate deposits. I used the runoff data from SMHI, for example. But if I only use the LiDAR data itself without any other data, the model was only 1% worse. So almost all the information about the location of soil moisture can be extracted from just the LiDAR, nothing else. I think that's pretty cool. Before I finish though, there is a bit of an issue with machine learning, especially when government agencies like the Swedish Forest Agency have started to implement this map and are basing their decisions on this map, is that it's sort of a black box. The map is not perfect. It has an overall accuracy of 86%, but the user don't really know when it's not accurate. So they just have to trust it blindly, which they do. So now the government agencies are basing their management decisions on this map, which is a black box, and they can't really explain what's happening. I mean, sure, my mom don't understand a normal regression either, but when you say it's used created with AI, people suddenly get a bit worried. And the whole Swedish system is based around trust towards the agencies. We especially noticed that during the pandemic. Sweden didn't implement any rules or new laws, just the agencies recommended people to not gather up, and people more or less follow that recommendation. But if you start to distrust one agency because they're using AI, that distrust could go over to other agencies as well. So I think we need to be careful when we implement AI solutions, even though they might seem like a good solution. I'm not saying we shouldn't do it, just be transparent and be careful with it. I just want to finish up saying that this is just one of my projects. I use similar methods to map soil types as well. Soil texture works well. I also transitioned to deep learning to map things like broad culverts, cultural remains, ditches. With that, thank you.
Thank you for the invitation to be here, and also thank you for the nice presentations beforehand, which were giving us nice overview on the issues on larger scale. Now we kind of zoom into a bit of a smaller scale where I'm giving you an example where we actually use this data to model things, and we are pretty much relying that the data is there already quite okay. So this was really interesting, David's presentation. But okay, so I put here a nice picture where we want that the water and the forest, they are quite nice looking, and we have the year water framework that the rivers and lakes should be in good ecological stages, or if they are not, we should improve their status. But very often the waters look like this. And why we need modeling here is that, for example, from the forested areas, I come from Finland, and the case study that I will be presenting, they are from Finland, but we have a lot of forests, and some years ago, maybe we were thinking that maybe the role of forests for the nutrient leaching and for the quality of the waters is not so big, but actually there is quite a lot of nutrients leaching from the forest areas, and different kind of things influence. So the operations that we do in the forest and their intensity, they affect, and also the site topography, the position relating to the receiving water body. In Finland, we have a lot of lakes, so basically quite many forests are always close to some water. And then also the soil type and structure, the groundwater table depth, and also weather conditions, how much there is runoff, how much there is precipitation and temperature, how the forest grows, and also then in a larger scale, the climate change impact on the changing runoffs or maybe the droughts. So we are approaching this problem of using this kind of all openly available spatial data, and we have developed this sort of a distributed spatial hydrological model, and it calculates the hydrology in a daily time set and within this 16 times 16 meter grid cell, which is based on the kind of multi-source national forest inventory data, which has been made based on the national forest inventory plot, and then with remote sensing data, we have been able to get this gridded data covering the whole country. And then we use also other type of data. The qualities and the accuracy is what it is, but then we are putting that together, and also the weather observations. And then we calculate the water balance in the 16 times 16 meter grid, and then usually when you do hydrological modeling, they are really computationally heavy, because they are maybe the water table level is calculated very accurately, and they are communicating the grid cells between themselves. But this is the solution here is to use this sort of a scaling of the topographic wetness index, and so we can kind of model the daily variation in the soil moisture. But it is computationally a lot lighter, because they are not kind of the water is not the water flow from one grid to another is not solved for every time step. But it's nice, it's an open source model and open source data, and it's kind of applicable to forested areas as well, at least. And then on top of that, we have other people who have also developed on top of that spatial hydrological model. We have moduled kind of approach. So we solve the nutrient balance in that same 16 times 16 grid, and then we calculate the export to the catchment outlet, and we see that how the nutrients and so how the forest grows, and then how the bacteria or other decomposition factors release nutrients, and then how the ground vegetation might take up the nutrients, and we can calculate so that what is the export load. And we can also put there, if there is a forest clear cut or a thinning, we can put that on as a spatial data there and see what happens. It's a kind of it of course like simplifies a lot of these things, what is happening in the forest, but if you look at the picture, it's still quite complex anyway, so there is lots of things that is tried to be kind of addressed in the model. So I will present here 3 case studies from this subcatchment. It's located in Lake Puruvesi. It's in the southeastern part of Finland, and it's the whole lake area is part of nature. Nature. I don't know, the network. This sort of like pristine, clear lake area which is protected. But then there is on the catchment there are these areas where there's heavily drained peatlands, and there are lakes that are very in poor condition, and they have actually even deteriorated the stages. So we are looking at this sort of small area there, and in that even is forming about of 33 subcatchments, and we are using that model to each of these and then try to make some conclusions about the role of the extreme weather for nutrient export and compare that to the role of the clear cut. So kind of see what is more important, and then the role of location of clear cuts, and then also the intensity of cutting. So we want to use this model and this open data to get answers to these questions. And first, the most important factor in this is probably the extreme weather. We gathered this is actual observation, but we gathered from an real observation data years that are really extremely dry or extremely wet, and or then this sort of wet and mild. So the winter time has been very warm, so there hasn't been that much snow cover, and then we also look at the data, so the actual forest data. What is there? What are the forest stands that are near or mature enough so they could be clear cut? And in Finland, most of the forests are privately owned. So even though not all of the forest would be cut at the same day or same year, but technically it's kind of possible if everybody of them decide that now we cut the forest. But these are extreme scenarios. But we just wanted to see the scale, how they influence on the nutrient export. And here you see on the left there is the nitrogen, and then on the left, on left nitrogen, on right there is phosphorus, and then in the picture there is the baseline is here, and then the different weather scenarios: dry, wet, and mild. And then here with the blue one there is the no clear cuts, so no additional clear cuts, and then the extreme clear cuts. And it's visible here that compared to the baseline, the weather extremes, they kind of drive the nutrient leaching. So if there is wet and mild, lots more runoff outside the growing season, then there's lots more water to kind of plug the nutrients away. But then on the other hand, on dry years, water is not flowing that much. Of course, the nutrient don't get exported either. And from here, you see that the area where the above average nutrient leaching increases, the effect of the weather is much higher. So it's kind of like like very extensive effect, and more than the clear cuts. This one was for the phosphorus, but same kind of trend in that. But okay, so the climate and the weather kind of drives the system, but we still have something that we can do. So we also use this model to we generated 100 equally probable logging scenarios. So there was a lot less of these clear cuts involved, but still quite a lot of and 100 different ways of locating those. And then we looked at how that affects on the nutrient leaching. And overall, there was about 47% change in the nutrient leaching. But when we look at all the 33 different subcatchments, this is for the nitrogen and this is for the phosphorus. But you can see that these are each of the are one of the subcatchments within this area. There are large variations, so we can influence with the location of the cutting really influences. And here is just two subcatchments that we can compare. That in one of them there is 17% of the area is cut, but it's located differently. So we can really get a difference in the nutrient leaching as well. Or then there is a lot smaller area cut, but it's still like very different. So they differ in area, but still they kind of produce almost the same kind of nutrient leaching. So there is this kind of ways that we can use the data, the open spatial data, there's modeling we can use to at least see what kind of probably nutrient loading we can get, or then to kind of try to identify and target the locations more. And then we looked at also this intensity of cutting. So we used we first looked at the data that where we have data that is the forests that are on peatland, and that the fertility class is herb-rich heath forest or mesic heath forest, so kind of like on the more fertile part of the forest type. And then also that the forest is mature enough for harvesting, and then that you can still harvest some trees, but the remaining tree volume is over 75 cubic meter per hectare. But anyway, so we found from the area that okay, there is about now, like currently there was 76 hectares of that sort of area, but in the future the next stands that are maturing, there is a lot more. And we found out just by using this data that okay, maybe we do a clear cut, or then we do just a less intensive thinning, we can see differences, of course, on the nutrient leaching. And these only kind of are related to that there is more vegetation that is taking up the nutrients. But yeah, to conclude, there is the role of weather is very important, and in the future, this is just a picture showing one extreme scenario though, but for future climate that it seems that okay, the temperatures rise, maybe also the forest growth increases, and overall the forest like nutrient uptake might increase, but then also these the precipitation is increasing in the areas where the kind of outskirts of the growing season, which is always a problem for the nutrient leaching. So we have kind of a problem there, but also then we have like possibilities to influence on the forest management. So target areas that are important or hotspot nutrient leaching areas, and you know, give guidelines for maybe wider buffer zones in those areas and something like this. And always when we thought of use this sort of data that already combines a lot of uncertainties when you look at when combining all this data, then we put that to a model which already simplifies a lot. So we are accumulating the uncertainty, but kind of the multitude of factors we cannot look at it otherwise than trying to do this and being open about it, open about the uncertainties. And this the models are open source, the data is open source, that it allows that when somebody else uses the model, then they might notice something like, hey, this is calculating this wrong, so we should maybe improve the model. So I think there's at least that kind of positive things. Yes, I think that was it. Thank you.
Hello, everyone, and thank you for the possibility to be here and for nice introduction. And yes, just to repeat a little bit Anita's speech, cultural system services are certainly those contributions of people to people which are non-material and hard to grasp, quantify, and map because they are everywhere and nowhere at once. And I would like to start with cultural nature system services. Recently, we had a Eurovision competition in which we got quite an interesting situation in which the public jury. So there was the public and jury or expert evaluations, and while the winner got a lot of scores from expert jury, public assessment was not that beneficial for this artist. It means that public opinion matters. Despite the fact we all know they're experts, especially in the music industry, the discrepancies between their opinion and opinion of regular people can be really, really drastic. So to address this, several methods are being applied in ecosystem services research, and the surveys or questionnaires and other deliberative methods allow us to get really deep insights into the quality of people-nature relationships, but they are often not especially explicit. We cannot derive maps usually based on this data. Participatory GIS, which will be discussed today, I hope as well, already provide a step forward. They provide also quite deep insight, but the learning curve of participants is something which limits their applicability in wider scales, for example, across the country or at a continental scale. So this is the place where social media data comes handy because it can be applied from the local to nearly global scale, while of course we need to compromise it maybe just because we need to use various proxies and nuanced techniques to get useful insights from this data. Nevertheless, social media have become a renowned and prominent source of data in various applications, mostly focusing on sustainable development goals which are related to urban quality of life and planning, and then health of the ecosystem, life on Earth. But the problem with this kind of settings is that when we come to the ecosystem services assessment, which has, as Anita also now says, this kind of three fundamental components: potential or supply, then flow of ecosystem services, which is the actual use of some services, and then demand from the side of beneficiaries. They are often applied based on data which is not accounting for public opinion. For example, in this pan-European study of ecosystem services, which was published 2 years ago by European Commission experts, the potential of ecosystems to provide recreational ecosystem services was simply based on expert assessment, and from Eurovision we kind of know that it might be biased. At the same time, the actual flow of nature-based recreation was surveyed in situ and provided nice data for the month and from population density data. How social media can help us to map all these components of ecosystem services assessment when it comes to recreation? Well, one study recently showed that combination of several social media sites, like it can be Flickr, Twitter usually, sometimes Instagram and YouTube, etc., improves the quality of vegetation accounting. So what we certainly know that social media are providing us a robust proxy for visitation accounting. At the same time, it is not everything what we can learn from social media data, because when people just visit some place, it's already one step. People came to some place and selected this place among other destinations. Then people took some photos or wrote some text about this place, and when it comes to photos, selected some photographs to be shared online. In this way, photographs and other media files online, when they're geotagged, they represent attitudes and values and opinions of people about their landscape experiences and outdoor recreation, etc., etc. So social media data is a complex source of insight, complex insights about the quality of people and interactions. And from the point of view of theoretical information, it contains three kinds of information. The syntactic one is simply about aesthetical values of nature. Pragmatic ones is about affordances of nature or outdoor activities which can be held online. And semantic information is all the textual, usually narratives, or also maybe visual narratives via Instagram, but somehow semantic information which is contained in the social media data. Okay, so we kind of now know that social media data is useful, important, and relevant. What about remote sensing? Remote sensing actually has been overlooked quite a lot in landscape studies, like in the studies of cultural ecosystem services and aesthetical studies. Usually, like in one study, also reported that in urban cultural ecosystem services domain, 75% of the studies simply use land cover as a product from remote sensing data, and also like 16–17% also use NDVI. In fact, remote sensing can be used much wider than that, and in one of the earlier papers, I showed that psychological predicates or psychological discourse and terminology also has its parallels in remote sensing. For example, when we're talking about the visual diversity of landscape, it can be estimated with entropy metrics in remote sensing. Then when it's about spatial relationships, for example, we can talk about landscape pattern, etc., etc. So there are certainly parallels between how people think in their real life and real nature perception and how remote sensing is designed. So what I'm advocating for here now is the united, a hybrid approach to assess and quantify and map cultural ecosystem services, which consists of remote sensing part, which is responsible for ecosystem services supply part, and then social cultural part based on social media data, using which we can evaluate the whole set of components of ecosystem services assessment. There are already some studies which confirm such a research gap in literature, because when we compare, they call it passive sensor, but remote sensing data in ecosystem services studies, it's vaguely connected to social media. Just a few studies actually done that, and not to the last extent. It might be to the reason that simply experts have different backgrounds. Remote sensing experts usually work with very hard stuff like LiDAR, I don't know, data, etc., while social media are mostly used in like in more humanitarian soft contexts. But I would like to demonstrate that it's not that bad, and we actually, on the example of Estonia, we've done a national-wide assessment of cultural ecosystem services. For that purpose, we used crowdsourced content from Flickr and Wiki on social media relevant for Estonia. We collected data in approximately 2000, like in 2020, and when we removed all the non-relevant photographs with computer vision techniques using the commercial platform called Clarify, we were able to distinguish between three main clusters of photographs which represent the use of cultural services. It's namely landscape watching, about photographs which do not contain any people in the short frame, but rather contain some kind of view or landscape. Then outdoor location depicting people engaged in different activities, as well as wildlife watching representations of biota at organism and community level. These photographs were geolocated, so we were able to map them, and obviously coastal areas and major cities are the main, say, spatial concentrations of their taking photographs representing cultural institutes. When we add one more step and calculating distance from the populated areas and count number of photos, we can already distinguish the territories of the highest demand, which because people traveled quite a lot sometimes to get to this location, for example, in southern Estonia or in Soma National Park, and took photos there. It means it's indicator of people's interest. And when we add some remote sensing data and population data, as well as land use land cover, by the way, produced by Polish authors for the whole Europe in 2017, use Sentinel-1 backscatter and Landsat data, as well as visual surface models, we were able already, this population data, count the accessibility of the photographs, let's say, so it was the simply clusters of distance between the populated, the cells of population grid to the photographs. And we found that, of course, major cities have the highest accessibility, but interestingly that, for example, southern Estonia for wildlife watching comes quite highly accessible, and actually like the major part of Estonians live in hotspot of high accessibility. While when we used remote sensing data, we created 526 predictors based on this remote sensing data which I described, and out of them we retained only 21 predictor based on multi-linearity check, etc. And I'm presenting here the most relevant indicators for ecosystem service, and we can see that, for example, mean near infrared reflectance values calculated using 21 pixel floating circle indicate negative relationship to landscape ocean, meaning that large areas of vegetation, maybe dense forests, so I don't know, crops might mean that they are less interesting for landscape ocean, while, for example, different entropy or diversity of color saturation, it has positive relationships to landscape ocean. So the diversity of colors, it has positive meaning to landscape appreciation. As for outdoor recreation, still kind of the diversity of color saturation has positive relationship. At the same time, the clusters of Sentinel-1 backscatter and luminance indicate that there could be some optimum in the patch sizes of landscape. So they should not be too small or too large, so somehow medium-sized landscape patches are the most preferable to maybe those allocated close to the cities are the most relevant for outdoor recreation. And for all these models, we got area under curve is about 0.9. And interestingly, that when we tested several machine learning algorithms, like here, then max and linear regression, random forest, and boosted regression, spline, etc., then Land of forest was the best performing model in all the cases, except for example, sometimes bush regression trees were higher for training, but lower for testing validation split. So we always refer here to the test validation split, and then Rainbow Forest behaves much better in terms of cover fitting. And Maxent is usually the second choice. And wildlife watching is the third service. I would like now to proceed to maybe the most interesting part is that out of this analysis, we received the predicted environmental suitability or environmental supply of cultural ecosystem services for each service. And obviously, it shows also like populated areas, coastal areas, etc. And what is the most interesting is that when we calculated the environmental supply within the self-population grid, we were able now to check that actually already not 50% of Estonians, but up to 70% of Estonians live in the more or less areas of high visual quality. So the majority of them, and only a minor part of people in mostly internal parts of the country, which may live in the villages surrounded by agricultural field, etc., have less, according to our data, opportunities to see something beautiful, etc. While it, of course, does not mean that this landscape are ugly. It just means that these places need to be further studied. How the future of the studies can be. We can check also or take into account various dimensions of human life. For example, socioeconomic characteristics. When we are talking about social media data, so we can check who are the people who are living this digital footprint online and who are the people using various ecosystem services, what is their income or social status. Also, we should take into account that population is not static, and some people's lifestyles, like cross-border commuters' lifestyles, can mean that they are exposed mostly to the landscapes on their work trips every day. At the same time, we now witnessing the enormous amount of evolution of land use land cover models, and this is the land use land cover model of Kharkiv region close to Russian border, which now shows that there are huge land use land cover changes and other drastic events besides the war, like wildfires, etc., urban sprawl, means that land use land cover changes can influence the way how people use cultural ecosystem services. Also, remote sensing data can be used to quantify landscape quality indicators like landscape coherence, which is the metric in which shows to which extent the diversity of landscape as a whole exceeds the diversity of its components. And in one of the studies, we show that it has a positive relationships to landscape preferences, as well as satellite imagery can be used to convert red, green, blue bands into the hue saturation value, for example, color system, which can be basis for color harmony estimations. And color harmony is higher for wetlands and forests, here on example of Estonia, and the lowest for the cities, meaning that we can actually grasp aesthetical value of nature with remote sensing, and this is highly underestimated, I would say, powerful tool. Of course, social media data are also changing, and recently they are changing API, etc., so they become less accessible for researchers. But fortunately, new tools like Telegram are emerging and providing new opportunities to collect data, for example, in the way how participatory GIS are using. And now I have work in progress. I'm testing now bots with the photos of my cat, which would allow me to collect people's feedback with informed consent. So GDPR is certainly covered here about the quality of their landscape experiences. So to finish, of course, the future of social media data and remote sensing studies is that we have a way for a rapid and wide, nearly global assessment of cultural and services. If we have all this computing capacity, etc., we can go way beyond of uncover and greenness and account socioeconomic parameters and mobility of people, as well as we can already this for example Telegram and other tools overcome the issue of validation of our findings. Thank you for your attention.
My name is Ewelina Dobrowolska, and I am Earth observation scientist working in Serco in Italy and providing scientific support in terms of scientific projects exploitations in ESA in Frascati. It is a very big pleasure for me to give my input to this session today. And I really regret that I cannot participate with you on site, but I have another workshop going on currently here in Frascati, so I was not able to join you in Poland. So to link to the topic of this conference, I thought a bit of introduction and exploration of the broad field of Earth observation data, particularly demonstrating the capabilities and applications of European Copernicus program in environmental research. And as you may have already discovered from the previous presentations, there is an urgent need for timely monitoring of forest ecosystem. And Earth observation provides that opportunity to observe forests, and not only at global scale, but also continuously without interruptions. So this brings me to Copernicus program, which is the component of the European Union Space Program that looks at our planet and its environment. Copernicus covers 6 major fields, and those are climate, land, oceans, atmosphere, emergencies, security, at different levels, ranging from global through regional to local scale. The Copernicus space component comprises of 2 types of satellite missions, 6 families of satellites dedicated to Copernicus, and those are the Sentinels, and 30 contributing missions from national, European, and international organizations. The program is coordinated and managed by European Commission, and it is implemented in partnership with the member states, the European Space Agency, the European Organization for the Exploitation of Meteorological Satellites, EUMETSAT, the European Center for Medium-Range Weather Forecast, ECMWF, and EU agencies and Mercator Oceans and others. So just very shortly, I will give you an overview of existing Copernicus Sentinels missions. So they carry a range of technologies such as radar and multispectral imaging instruments for land, oceans, and atmospheric monitoring. And the Sentinels are Sentinel-1, which is placed on a polar orbit, and it is all-weather day and night radar imaging sensor, which serves for land and ocean services. It was launched on 3rd of April 2014 as a first Sentinel mission in the orbit, and then it was followed by Sentinel-1B on the 22 April 2016. Unfortunately, the life cycle of Sentinel-1B ended on 23rd of December 2021, and now we are waiting for the launch of Sentinel-1C. Sentinel-2 is a polar orbiting multispectral high-resolution imaging mission for land monitoring to provide, for example, imagery of vegetation, soil, and water cover. Sentinel-2 can also deliver information for emergency services. It was launched on 23rd of June 2015, and the second Sentinel-2B followed on 7th of March 2017. Then we have Sentinel-3, which is a multi-instrument mission to measure sea surface topography, sea and land surface temperature, ocean color, and land color with high and reliable accuracy. Sentinel-3 was launched on 16th of February 2016, and Sentinel-3B joined its twin in the orbit on 25th of April 2018. Then we have the Sentinel-4 and 5, which will be the instruments carried on the next generation of meteorological satellites. And Sentinel-4 and 5 will provide data for atmospheric composition from geostationary orbit and polar orbit. And then we have also Sentinel-5P precursor to fill the gap between NVSat and Sentinel-5P. And we have Sentinel-6, which is a radar altimetry mission that provides a measure on the global sea surface height, primarily for operational oceanography, but also for climate studies. Okay, here just very shortly some more details about Sentinel-1. So as we said, it is a radar mission with C-band synthetic aperture radar at 5.4 gigahertz. We have twin satellites. We had twin satellites. Right now there is only one satellite on the orbit. The life cycle of one mission is 7 years with possible extension. And data are provided in single or dual polarization, which is particularly useful for forestry. And data are required in 4 different operational modes. And for land monitoring, we are using mostly interferometric wide scope, which is bolded here. Street map is used, but only for emergency management. Then we have Sentinel-2 mission, which most of you, I think, are familiar with. So it carries a multispectral instrument with 13 bands from visible to the shortwave infrared part of the spectrum. And similarly as the other Sentinels, it consists of twin satellites in the same 10-day polar orbit with 180 degrees of separation. And the bands are acquired in 3 different resolutions, as can be seen in the table below. So the visible bands and the wide near-infrared bands are available in 10-meter resolution. The 20-meter resolution is dedicated to the vegetation, red edge bands, and shortwave infrared bands. And 60 meters bands are applicable for the band 1, 9, and 10, which provide information on cloud and atmosphere. So Sentinel-2 serves a wide range of applications, and while we cannot name them, all of them, the main ones are in the domains of land and vegetation monitoring, and we will have a look on those applications very soon. Sentinel-3 carries a suite of cutting-edge instruments to systematically observe Earth's ocean, land, ice, and atmosphere, and permit, for instance, the weather forecasting. The revisit frequency differs based on the sensors. It provides revisit frequency of less than 1 day, for example, for ocean and land color instrument, and sea and land surface temperature radiometer. OLCI instrument provides information on global vegetation index or fraction of absorbed photosynthetically active radiation in plant canopy. And SLS-TR provides biomass burning information. So, for example, it can be used for wildfire detection and surface temperature monitoring as well. Here are the remaining missions, which I put a bit together. So Sentinel-4 and 5P, as I said, are applied to atmosphere monitoring. And those are based on passive imaging spectrometer. And Sentinel-6 carries a radar altimeter to measure global sea surface height. Okay, so Sentinel-1 data has been used for an ever-expanding number of applications over many thematic domains, such as forestry, agriculture, and urban mapping, and also emergency response. In forestry, it includes deforestation, biomass estimation, forest type classification, and burnt area mapping, for instance. And open access to EO data from Copernicus Sentinel missions has provided researchers and practitioners with a wealth of information, allowing for precise monitoring of vegetation, estimating biomass, and detecting disturbances in the forest. As a first example, I will provide an ESA-led project, Sentinel-1 for Science Amazonas, and it has processed billions of pixels over the entire Amazon basin, and converted it into a data cube, helping to detect forest loss. This research not only showed the traditional approach of using Sentinel-1 data to detect forest loss, but also the way the data process is novel. By organizing data in data cube, which provides a simple way of organizing and viewing any sort of data with multiple dimensions, some of which are associated with space and time, it can help gain insights into the patterns and trends that might not be immediately apparent otherwise. So from January 2017 to November 2021, the team, after processing more than 450 terabytes of data, detected forest loss of over 5.2 million hectares, which is roughly the size of Costa Rica. So those pixels of the Sentinel-1 satellites represent 20 per 20 meter of forest, and they're harmonized under the SatCube design. And with a simple thresholding approach, we can detect forest loss in which is demonstrated here. And the current results are also available in the project website, in the dedicated viewer, where you can see also by tile the area of forest loss in a time span. So here you see a forest loss in 5 years from 2017 to 2020 in a selected Sentinel-1 tile. Here you can also find a QR code to access these results. Another example of forest loss in the tropic is provided by SOFT project. So with SAR data, it provides near real-time forest loss maps over Vietnam, Cambodia, and Laos, using Sentinel-1 data to the users of public sectors to support their efforts to control logging and log trade. So cloud cover SAR images have great potential in tropical areas, and Sentinel-1 constellation offer a unique opportunity to systematically monitor forests at global scale. Here the visual comparison of forest loss detection result is present, highlighting various sizes and distributions of disturbed areas. Intact forest and forest loss reference data are drawn in green and red respectively. So here as well, I provided you a link to the source of this research results, which are publicly available on EO for Society website. And here we have another example with a very recent story published a few weeks ago. And here we can see the benefits of using raw Copernicus Sentinel-2 data and artificial intelligence to improve response times in early warning systems for catastrophic events. So the traditional data handling paradigm is optimized for ground processing, but is not always well suited for early warning applications, where latency is crucial. So while high-level products such as level 1C are calibrated, auto-rectified, and include the band cover registration, these features are not always necessary for specific applications that prioritize rapid response. And to fill this gap, the research team created a data set of raw Sentinel-2 data for the detection of specific events, such as the thermal hotspot created by bushfires. A team of researchers working at ESA-ESRIN in ESRIN in Italy have been investigating the benefits of using raw Copernicus Sentinel-2 data directly instead of this traditional processed satellite products. And this novel approach is public now, so you can find here below the link to the publication. And this is also publicly available as a web story in the ESA website. Okay, another application with the use of Sentinel-2 data shows the findings, which are really recent as well, that demonstrate the important carbon value of conserving, recovering forests along with protecting old growth forests. And this new research has been published in Nature, and it was led by the University of Bristol and Brazil's National Institute of Space Research, and showed how degraded forests and regrowth of secondary forests in previously deforested area are annually removing at least 107 million tons of carbon from the atmosphere across the tropics. The sink is approximately equivalent to counterbalancing half of the annual fossil fuel emission from South America. And lastly, Sentinel-3 data in forestry is also used. And here I have an example of application, how it is used for wildfire detection and monitoring. So the thermal infrared sensors on Sentinel-3 detect hotspots, allowing for early identification of wildfires and assessment of their impact on ecosystems. And global fire occurrence data is available from 2016 onwards. Right now, the European Space Agency has opened the Sentinel-3A World Fire Atlas, which also is possible to access. It comprises 2 informative pages. The first offers insights into the worldwide distribution of single nighttime fires detected at both country and global levels, and simultaneously in the second page features an interactive dashboard allowing users to explore and analyze statistics in a user-friendly manner. So these results are based on Sentinel-3A as well as TR level B, non-time critical products. So following the launch of the latest missions, Copernicus Sentinel-6, the focus is now on the future. So very useful missions for the forestry sector will be for sure CHIME, so it's Copernicus Hyperspectral Imaging Mission for Environment, which would carry a unique visible to shortwave infrared spectrometer, providing routine hyperspectral observations to support new and enhanced services for sustainable agriculture and biodiversity management. And the next one is the land surface temperature monitoring, which responds to priority requirements of the agricultural user community. And the last but not least, ROSE-L, which would provide additional information that cannot be gathered by the Copernicus Sentinel-1 C-band radar mission, since it would carry an L-band instrument, SAR, whose longer L-band signal can penetrate through many natural materials such as vegetation, dry snow, and ice. And we have also Earth explorers that are pioneering scientific and technical missions. And for the forestry, the upcoming Earth explorer missions are for sure biomass, which would concentrate on forest carbon, and flex, which would allow to explore the photosynthesis in plants. Here I also provided a slide about where you can access the Copernicus data for free. As I mentioned, Copernicus missions provide data for all users free of charge. And here is the new data space ecosystem where you can access the data. Also, I added here a slide about Copernicus land monitoring service, which is very useful when we talk about the vegetation and the canopy cover, canopy reflectance. So you can also explore these data sets, which are also available on the website I provided here. And they have global, regional, and European coverage. Platforms and opportunities. So we have more information about the ongoing projects and activities, which are continuously updated on EO4Society website, which is the first platform I show right now. Then I would like to also mention the carbon science cluster that engaged the carbon community in ESA. So you can also explore that website and join the network if you have project funded by ESA, for example. I also placed a platform for young researchers to explore. So this is the forestry TEP platform, which offers to the users satellite data and computing resources, and also the forest analysis tools and sharing and interfacing features. So you can also explore that one. And ESA Climate Office provides also access to biomass datasets and as well as vegetation parameters, which has been released in April. So you may also discover that. About knowledge and sharing and learning materials, more training materials are also available in the website I placed here, so EO4Society ESA.int. And in the resources, you may find still the materials coming from Copernicus Research and User Support Service, which aim to develop online free access platform to promote the uptake of Copernicus data and support the scaling up of educational and R&D activities, in particular services provided to Copernicus data and cloud computing. So you may also check, I had also there one webinar or two, so you can also explore. The one is on the forest above ground biomass with Sentinel-2 data in Python, so you can also watch it. And all the materials and training kits are also available for free to use. So some last remarks. Open access to Copernicus EO data from Copernicus Sentinel missions has provided researchers and practitioners with a wealth of information allowing for precise monitoring of vegetation, estimating biomass and detecting disturbances in the forest. And millions of gigabytes of SAR and optical data are required both day and night, regardless of cloud cover, haze, smoke, or aerosols, allowing deforestation and forest degradation to be monitored at least bi-weekly. So the challenge lies in finding adequate methods to extract meaningful indicators of forest loss from the vast amounts of incoming radar data, such that the anomalies in the time series can be regularly and consistently detected across the forests. So such forest monitoring methods should be transparent and easily understandable to the wider public, enabling confidence in their use across various public and private sectors. So with that, I would like to thank you all for attending. I hope I did not went beyond the schedule. So feel free to contact if you have any questions. I am available under the email below. And I wish you a very nice continuation of your conference.